back into my groove. Hello, Eric.
Hello, sorry.
How are you doing?
Lost you completely there.
Oh, no problem. I was just literally doing the sort of introduction welcome to everybody. So thank you, Eric, for joining today as well. So yeah, as I was saying, so ASHRAE, we were formed in 2018, and it represents one of many chapters within the region 14, which covers UK, Europe, and Israel, and is one of more than 180 chapters worldwide. It is the chapters and their volunteers that provide the grassroots to the ASHRAE worldwide organisation, and this Society Year Presidential Address focuses heavily on grassroots. So student volunteers are essential to this, and after all the challenges we face with global warming and mitigating future pandemic risks, very much rests with grassroots of society and the next generation of HVACR professionals to collaborate and innovate solutions to find a way through. And as a chapter, we remain fully engaged with students and universities and welcome students to get involved at their respective universities and form a student branch or branches. This year's UK Midlands chapter is looking to send students to ASHRAE 2022 Winter Conference in Las Vegas, where they will be able to network and attend valuable workshops and seminars. And we also support students with ASHRAE's Smart Start programme, which takes those with over 1 year's of ASHRAE membership. We can move them and help them to get to associate member, and therefore they'll enjoy all the benefits such as access to standards. As I said, growing as a chapter year on year, providing value to our members, and we're always looking for volunteers and to encourage students to join ASHRAE and the chapter, because there are many opportunities on the Board of Governors, for example, such as young engineers in ASHRAE, student activities, and many more. And it's with the support of volunteers that we can all collaborate and work towards ASHRAE's mission, which is to serve humanity by advancing the arts of science of heating, ventilation, air conditioning, refrigeration, and their allied fields, and with the vision of a healthy and sustainable built environment for all. So a big thank you to all the students for their time, hard work, and preparation to present today. We can imagine it's taken quite a lot of work. We have a wide range of topical presentations to look forward to, and with prizes and certificates available to all students. We would like to thank our judges from industry attending today, and thank and recognise our sponsors, IES, Hilsa Moran, Kingspan, Bizria, Vexo, Vispa, EcoSense, Train, Wes, and NSIMS. And a thank you as well to our ASHRAE Life members for joining us today. Well over 30 years of membership experience, so we look forward to your insights and anecdotes, no doubt, later. Very valuable, certainly for new members to ASHRAE. And we'd like to also thank Frank Mills, who's our distinguished lecturer today, and we'll be presenting after we've received all of the students' presentations. And finally, a thank you to Andreas Sepulveda, who joins us today. He's the Region 14 DRC, heading up the region, and all the chapters assigned to the Region 14. Andreas has been our regional director since, I believe, 2019. And I would now like to welcome Andreas to the Student Competition 2021. And Andreas is going to introduce Region 14 and also present certificates in appreciation to our Life members. So thanks again, and thank you, Andreas.
Well, thank you very much, Darren, for your nice word and your good explanation about what ASHRAE is all about. I think that for me, I'm delighted and very pleased to share time with Life member on one side and also with the students, talented students. And I'm looking forward to hearing for their resume or the presentations. Well, Region 14 involved, as you said, and that because I'm repeating what you said, is UK, Europe, and Israel. So, and there are 9 chapters, but all in all, there are also members who are not under a chapter umbrella. So all in all, I think that we are close to 2,000 members. With a lot of activity, the region was formed in 2017, so it's a quite a young region, the youngest. And I'm very pleased because we have a lot of initiatives and particularly from the UK Midland chapter. You know, you are very entrepreneurial, you have a lot of initiatives, you have always a smile in your faces, and it's very nice and very rewarding supporting you. And I hope that that we are very much engaged, and because your people, your members are very much engaged, and we hope that we are at the level to support you going forward. So I'm not going to spend more time. You know that we have in a couple of weeks what we call the CRC, which is the Chapter Regional Conference. That is a special event organized by each ASHRAE region on a yearly basis. So you are most welcome to attend it. We will have some ideas, sharing ideas, and also we will be hearing for all chapters. So I think that, well, let me take the opportunity to invite you, all of you, to participate. I don't want to spend more time about Region 14, but I'm honored and delighted to hand out those certificates of appreciation to a few and very special ASHRAE members who contributed that much to the growth and progress of the society. So all of you who are going to receive this certificate of appreciation, most welcome to this prestigious and exclusive ASHRAE Life Member Club. You have proved that it's worth being an ASHRAE member, and I would like to ask you to remember those people who fed your roots and encouraged you to join ASHRAE a number of years ago. Thank you very much as well in behalf of the society for your loyalty, and I hope that ASHRAE has contributed as well to the development of your career, and as professional you are much more honest and good ones. So congratulations to all of you who are going to receive this appreciation certificate. So I will start with, I don't know who, those of you presented, but first certificate of appreciation goes to Benjamin Trevor. Congratulations, well done.
Thank you, thank you.
Have the opportunity, maybe, I don't know if we have time, but I would be very pleased to hear and to listen to you about any anecdote or nice story you can share, but I don't know what is the, well, I'm not controlling and managing time, but congratulations. David Platt, I don't know if you're around. David? No? Okay, okay. Well, congratulations on behalf of the society. Derek Gilder, another young life member. No? Next. It was Nicholas.
No.
No? Well, congratulations. Ijas Shah, I don't know if I have pronounced your name, but I know you are around. So congratulations, well done. Next is going for James Sheehan.
Thank you.
Thank you very much. Congratulations. Well done.
Would you like me to say a few words?
Sure.
Thank you.
What?
I was starting a final year project at London South Bank University too many years ago, and I had teamed up with an architectural colleague from the Brixton School of Building, which amalgamated with London South Bank. We chose a brewery for our project. My tutor was very helpful and suggested I visit the library and study the ASHRAE manuals for the information regarding the brewing process, which I was very interested in, and the environmental conditions. I found the manuals full of practical advice and the information, the fundamentals, application systems, and refrigeration sections. I have been using the ASHRAE manuals for around 50 years and would recommend them as an invaluable source of project design information for building services engineers.
Okay, thanks very much.
Yeah, all done.
We'll come back to all the life members and share.
Okay.
Please. Okay. Michael Bates, I think that you are around. So well done.
Yeah.
Congratulations. You
Thank
are
you.
another young life member.
Thank you.
Neil Horsworth. I don't know if Neil is around. Well, congratulations. Richard Hosley. Well, congratulations. Roger Spur. Okay. And William Jackson. Okay, well, congratulations to all of you, and be very proud, because the society is very proud of you, and to be part of this exclusive life member club. Most welcome, and please keep contributing to our society. Thank you very much.
Andreas. Yeah, we certainly look forward to listening now and sharing their experiences for life members. So, and thank you, James, for sharing, really your grassroots and kind of when you really started seeing the value in ASHRAE and how that's helped your career over the years as well, and certainly what you're passionate about. So we'd love to hear from other life members with us today. If they'd like to share any of their experiences with ASHRAE to the younger members, and any anecdotes they'd like to share.
Yeah, I'm happy to talk.
Thanks, Trevor.
Do you want me to start?
Yeah, go for it. Yeah.
Oh, right, okay. Right, well, I'm perhaps got a little bit of a different background to a lot of other ASHRAE members. I started work aged 15 for a commercial refrigeration company, and after a year they offered me an apprenticeship, and I went to Willesden Technical College on day release, and I was also sent to various manufacturers, press cold, Kelvinators, Halls. When I first started work, in a lot of cases, we were still using methyl chloride as a refrigerant, which was an awful refrigerant. R12 and R22 had only just come in, and a lot of the equipment was still running on DC motors in more remote areas. So I spent my life working for refrigeration and air conditioning companies in a variety of roles: supervisor or engineer supervisor, service manager. In later years, technical support, training and quality assurance. I did 6 city and guilds in the 1980s, really to improve my knowledge, because I realised it was weak. And after a visit to Carrier in the US, I joined ASHRAE as an associate, predominantly to gain the information that was available via ASHRAE. I went on to deal with accident investigation and health and safety. But for the last 25 years of my working life, I worked for 2 manufacturers of close control air conditioning equipment, Liebert and Denko. And in both cases, I was initially the service manager, and then did the technical support and the training. My last job with Denko, I also got involved in quality control of the manufacturing process and the service department, and also environmental auditing. I was heavily involved in the design and compliance of close control units that used R410A, which superseded the previous R22 units. There were many problems with this, because the R&D department did not understand the requirements for dealing with a high pressure refrigerant such as 410A. My work took me all around UK and Europe, Germany, Italy, Spain, Finland, Denmark, Isle of Man, Germany, Jersey, Sweden, Libya, Turkey, France, Belgium. I could go on. Most of the countries in Europe were visited almost always to investigate faults that local engineers couldn't resolve. I worked in the trade for 53 years. I worked on shop refrigeration, cold stores, blast freezers, bulk milk tanks, mortuaries, breweries, military bases, low temperature test chambers, which were very interesting, submarines, absorption chillers, compressed air dryers, fruit stores, a lot of work on data centers, both air conditioning and mainframe cooling. I also oversaw the maintenance of air conditioning on a nuclear reactor site in Anglesey, and also did work at Pinewood Studios in the archive that's looking after the films. So I retired in 2014 after 52 years in the trade. My hobby has always been steam railways and narrow gauge railways, and my work all over Europe allowed me to visit many locations that I couldn't normally get to. So I would have an extra day and go and visit somewhere. I don't even know if my employers actually knew that I was taking a day longer than anything else. Since my retirement, I've been advising on air and ground source heat pumps for charities in Midlands, predominantly churches. In summary, with all my employers, there was a steady progression up to managerial roles, but the most job satisfaction I obtained was the engineer supervisor role. I learned to question a lot of people's technical decisions and advice, which were often wrong. I found a night's sleep would often solve a problem. If you're in a hotel somewhere remote and you've got nowhere to talk to, go to sleep and you wake up in the middle of the night and think about it. To finish, two things that helped greatly before mobile data was a box of maps in the car and a box of instruction manuals and wiring diagram. They were invaluable because without them you would be completely snookered, because every engineer has a habit of taking wiring diagrams and manuals in case they need them, so they're never there when you want them. Okay, thank you.
Thank you. Thank you, Trevor. That was a wide range of experience, but certainly centred more in that sort of, as you say, the refrigeration role. And you mentioned your grassroots sort of period in amongst that was ASHRAE, when you're getting aware of ASHRAE in those early days. And how have you, and did you find throughout your career with ASHRAE the sort of the updates that you would get and the standards and the sort of the educational platforms, access to information? How's your experience been with it?
Oh yes, I mean obviously the handbooks that come were a font of information. You could always get information in there. The breadth of the subject matter was quite astounding. And if you were confronted with a piece of equipment that you didn't have any concept about how it worked, you could sit and find it in the ASHRAE manual and gain an understanding. You know, one of the things that I was very puzzled with was working on compressed air dryers, and you have to go back to the basic principles of refrigeration, which is you can get from the ASHRAE manual. I used to purchase a lot of the standards. The only comment I would say in some cases, the standards don't apply or didn't apply in the UK. But it was very useful to have access to the information. Of course, once the internet became much easier to access, then you could go online, log in with your password and search for what you want. Yeah.
Brilliant. Thank you. Thank you very much.
Okay.
Michael, would you like to to share your experience and.
Sure. Yeah. I'm not sure how you're seeing me here, so I can only see you guys. Much like previous speaker, I started by mistake working in building services industry, just because air was in the name and I was interested in aircraft, but unfortunately it was air transfer equipment. But I started in 1961, that's 60 years ago this year, as a junior draftsman, and then just worked my way up and worked for various manufacturers, but just gaining information. I didn't have any very good qualifications when I started, and I was just learning on the job. But the kind of companies I worked for, we got very involved in air conditioning, and we had to design all the heat exchangers and everything else. So you got a good basics in, I mean, I could read a psychometric chart like the kids could read Nando's menus today. But that brought me on, but that took me along to about 1974, when I was fortunate enough to get a job at the British Broadcasting Corporation, the BBC, as a junior HVAC engineer. And that really was the start of my design and consultancy part of my career. And that's really when I think the career started off. But all the previous stuff I'd done with manufacturers really paid off, because I had a good hands-on understanding of all the equipment and the systems and everything else. So while I was at the BBC, come about 1979, I joined ASHRAE because I didn't have the good enough qualifications to join CFD. So sorry about that, ASHRAE, but they took me on board, mainly because it showed that I had an interest in the industry and that I was prepared to learn. And that became very useful to me, and why I maintained. And talking about the ASHRAE books, I was always amazed that you got a new one every year. And once I built up the set, I thought, well, I haven't got room. And there's quite a few companies around the industry now that have probably got full sets of ASHRAE guides, thanks to me, because you don't want to throw the old ones out. There's too much useful information in them. So I always felt that it was worth handing on to the companies that I was working for, whilst keeping my set up to date, of course. So that was a benefit to me for joining ASHRAE, and as I say, I became a member eventually, and it just was proof that I was interested in. I left the BBC in about 1985 because they were moving offices and I didn't want the kind of travelling, but I really enjoyed myself there and I'd learnt an awful lot. But when you worked at somewhere like the BBC, you only learn what you HVAC, for instance, for just tin and air, basically, because they had separate people doing pipe work and all sorts. And it was a bit worrying when I went into private practice that, of course, you have to do everything from air services to water services, even a little bit of electrical when it came to controls. So, but I had a good grounding in that. And as we said, ASHRAE was a great source of information because this was almost pre-internet days. I've seen quite a few changes then in the practice because we've had quite a lot of milestones in the industry. And I'm just thinking of them, things from moving from pneumatic controls to electric controls, electronic controls, like SAFER, I think is an old name. And you could work out, it was easier for engineers to work out the control processes rather than just handing it on. And you could tune what you wanted, because what we all talk about, what students talk about today, is energy saving. But even in those days, as engineers, we were trying to save energy, not because it was great for the environment, because it was good for the client, because he was saving money. So that was just one way that we always probably benefited the climate unwittingly, but that's how we did it. And with the advent of these controls, you didn't have to go for reheat anymore. You could do all sorts of things, mixing, which saved energy. But getting on to It's Never Too Late, we went through several recessions in the UK, and the building services industry is always very susceptible to the economy. And I found I got made redundant a couple of times, and I just felt it was getting harder to get a job. I never was out of a job, but I couldn't get a job that I really wanted. And I was working for some small one-man companies and a bit of contract work. I thought, this isn't any good. And I was lucky enough, I was able to enroll at the South Bank, I think it's London South Bank University now, and got on a degree course there and did a part-time course there, sort of working, doing 1 day a week at uni and working for the rest of the time. And that was a long, hard grind, because without the full school leaving qualifications, I had to do a foundation course. So it wound up as a 5-year course. But the nice thing about that course there was that if you faltered at any time, you could get your OND, your Ordinary National Certificate, I think it was then, Higher National, and then you could get your degree, and then you could go on to do the honours. And I was determined for the honours degree, because it was the last year that with that qualification I could get membership of CFD, which was the goal for me, because I appreciated ASHRAE, but CFD was always in the UK very much something that if you wanted to go for a job, you nearly had to have that qualification as well as having a degree qualification. So I graduated in 1998. So unfortunately, I only had 12 years of fully qualified work in the industry. But to be fair, I joined CFD in 2002, and then the next year, it was only a few months later, got the CEng status, and that made life a lot easier to get a job. But as it happens, I only worked for one company after that. But I think the interesting thing is you should never close your mind to what's going on. And once we got, I think it is in the mid-80s, late 80s, computing came in. We were using SciMap programs basically for calculation, and that was quite liberating, because we could do lots of variations. Previously, when you do it all by hand, you don't really want to make lots of changes because it's hard work. But with the computer programs and much more sophisticated today, you can start to do all your fine tuning, and you could help the architect with orientations and everything else. But you could give the architect really useful information in terms of energy usage of your systems that you're designing. And towards the end, I tended to specialise in hospitals and research establishments, laboratories. I did quite a lot of work on that, and that was very interesting. And in the laboratory work, again, ASHRAE was probably more of an interest, had more information than the CFD guides, because they had all these sort of system designs, and of course in the States they have these much broader they have many more of these areas than we do in the UK. So ASHRAE never went away in my use, as a useful tool and help, and CFD was a very complementary benefit because of our standards in the UK, and when you went to people, they understood more what CFD was, although after you had explained it was a bit different. But so all in all, I've got a lot from my ASHRAE membership, I would say that, because it gave me, in my mind, a little bit of status and encouragement. And I would say never give up. If you've got you've got a reason to do something like getting a degree, and I know all your students are probably starting at that point. If it doesn't quite work out sometimes, there's always a bit of time. That's what I say, but never close your mind to what's going on. And sometimes I looked at some of these people, don't be too specialised. Try and keep a broad experience, because you'll be far more useful to society if you've got a broader experience than if you're just trying to concentrate on one little aspect. And by the way, we really appreciated Liebert and Denko equipment because we used a lot of that equipment when we were doing mainframes and stuff like that. So we may have crossed swords at one time or another in the past. But I hope that's just enough information and an explanation. And all I can say is qualifications do matter, but they matter when you're looking for the job. They're not the be all and end all when you're learning on the job. And you should listen, you know, the students, this is to the students, listen to the people you're working to. Is that enough?
Yeah, thank you.
Thank you. Thank you, Martha. Brilliant. Do we have any other live members here? Just mindful that we're running a bit short on the time. Is there anybody here? Have you got anyone else on the list? I'm just trying to look online here. Anybody else like to talk?
Can I just say something to finish off? I got into the trade totally by mistake. At 15, my mother said, "You've got to get a job," and I did nothing for a few weeks. And then she said to me, "You're going for an interview." "Oh, am I, Mum?" So I trod along to this company. I didn't know what they did. I didn't know anything about refrigeration and air conditioning. And the chap interviewed me. At the end of the day, in interview, I said, "Well, will you let me know? Have I got the job?" And he said, "No, it's already been arranged with your mother. You're starting next Monday, and this is the pay." So I always blamed my mother for getting me into the trade.
Fantastic. Thank you, Trevor. It is funny, isn't it? Sometimes when people set out on a course you think that you're going to take, and somehow you end up in a completely different direction. But yeah. No, thank you all for your your experience, your insights and anecdotes. I think it's been extremely valuable, and certainly for the the younger ASHRAE members and the students as well. Without further ado, what we're going to do is move forward then to the presentations from the students. We have our judges here from industry. Thank you again, judges, for attending. And the first one, each student, just to give you a bit of a background, each student's going to present, but they only have 5 minutes to present, so pretty slick presentations to get through. And we're going to have a break. We're going to go through the undergraduate and master's presentations first of all. And just another quick count, because we had another one in. 1, 2, 3, 4, 5, 6. So there's 7 to get through. Look forward to those, and then we'll have a 10-minute break before we move on to the PhD presentation. So the first presentation, we'd like to welcome Shazia Dixon from Loughborough University, and her presentation covers kids' right to fresh air. So if we're able to load that up, and Joshua, if you're okay on the controls. And if judges, if you wouldn't mind having your scorecards ready. Thank you.
Yeah, just Shazia has to share her thing. Shazia. She's here. I mean, I made her the presenter.
Okay.
We can go with the second participant. Maybe we can bring in Shazia next.
Okay, so we'll swap around to so the next one is holistic sustainability from Apurva.
Yeah.
If I don't pronounce it, is it Gassais?
Yes. Yeah.
Thank you very much. If you'd like to share your presentation.
Yes. Is it visible?
It is, yeah. Not quite full screen.
Is it visible? Sorry.
So that's visible now, but there seems to be some sort of dark image cropping just the bottom right corner. I think it's on your side, not on mine. Let's have a look. I think we all can keep in mind that, yeah, when we're trying to do these things online, it all comes with some challenges. So take your time and no problem at all.
Is it fine now?
Can everybody else see that? I've still got this sort of dark cropped area, but I can just pretty much used to it.
Yeah, on the right side there are like some black like rectangle boxes or something.
So like,
If you are you able to try and are you sort of sharing the full presentation, because we can sort of see?
yeah, yeah, I'll try to do that. Just a second.
No problem.
I think you have to click view and go full screen.
Is it fine now? Because I'm able to open the PDF.
It's visible now. Yes, it's there's still the sort of the black sort of or dark cropped area, but we can see the full slides now. So that looks.
So should I continue with this one?
Someone says you can click Control Z to erase that effect. Control Z. Just click on the PDF and then click Control Z.
Control what?
Control Z. It's on the chat. You can see some people have given.
Yeah. Oops.
Maybe if you press the F11, sometimes that makes the like the page screen full. So
yeah, I'll try to do it.
Actually, I have shared my screen. So can you see the PDF now clear?
Yes, I can see.
Okay. Yeah.
That's great.
So start with this one.
Yeah.
Yeah. No. If you want a chance just to set yourself, I mean, we are actually doing okay for time. So if you're ready to go, then absolutely great.
Yeah. Hello everyone, I'm Apurva Ghaisas. I'm doing MSc in Environmental Design of Buildings at Cardiff University. So the topic which I'm covering today for the presentation is holistic sustainability. The word holistic is like balance and interdependence of like different components. So like when we say sustainability, when we say holistic sustainability, it is the correlation and interdependence, how each factors are like interdependent on each other, like how economy, so the three pillars of sustainability, which are social, economy, and environment. So when a holistic approach is used, how these three parameters are catered. So I would like, being an architect, I would like to tell the role of architect in holistic sustainability. So like there are, when we say holistic sustainability, there would be some limitations as well as some motivations, we can say. So nowadays there are things like green building certification and everything. So we get this different incentives, and so like we can in these two things are achieved, like there when it covers incentives sort of thing, we get there are economic benefits as well as environmental factors are concerned. So like to how this holistic sustainability is catered, I would like to present it through a presentation, through a case study. This case study is the second slide, please. Yeah, this is Drupagma Karpo School. This is a residential school in the northern border of India. The school is like in a very remote village, built for a specific community. The architects and the designers for the whole school complex is Aru, and the climate for the location is very cold and dry. The school was built on request of local residents, like the local people were requested the leader of the village to provide a good education and like basic facilities. So these all things came up with the idea of the school. Yeah, so here we can see on the right side what all holistic factors, like why this building is holistically sustainable, we can see that. So this design, it was based on traditional Buddhism, like a mandala, like using traditional values but placing the buildings in a certain angle so that it can get a maximum daylight and maximum ventilation. So like in these two things were considered while designing the campus. So we can see the exchange of finances and local community. So like all the local materials whichever are available were used. The architect has done a background research about the climate, the context, what is the local need of people. And so it was, as it is like the remote community, which is like it has a cold and dry climate, so 6 months of the year it is disconnected by the road or anything. So the local materials which are available were used, so this eventually reduced the low cost. And the local architects, it was not the modern technology which was applied on the design, it was in the background research they studied what are the local techniques and methods which were eventually used there. So it was like it encouragement, so the architects involved the local craftsmen and local skills were given importance, so this encouraged local employment there. So it was a platform for the like cultural exchange and exchange of knowledge and everything at a very local, from school children to the local people to the architect, like the architects team from UK. So eventually also there was environmental factors which were catered with, like the design was based on cultural values. All the passive strategies were implemented, like orientation of buildings was 30 degrees to the east. Then use of local materials, the landscape which was done, it was sustainable, like the local homegrown produced food were planned in the landscape. The sanitation the sanitation which was proposed was sustainable. It was the traditional VIP latrines were used. Then the Ladakh is a place where it has a scarcity of water, so like the water pumps were proposed. So yeah, so like in whole of this design, it involved local craftsmanship, it gave value to the culture and tradition. And next slide, please. Yeah, here we can see how it is, like the planning. And the first, it is a nursery school. So like to avoid extreme heat and extreme climate, there are classrooms and in between the courtyards are planned. So which also gives the extra space for the students, enclosed space between the classrooms. We can see the daylight used for the residential buildings. Trombolt strategy was used. Here we can see the solar powered pumps were used and for water. Also Ladakh is a place which like frequently have earthquake. So the timber frames were used, and it was analyzed through a software. We can see the resources like the stones and mud which was available, was used for the inner walls and external walls. The willow which is locally grown in the farm, that was used for the roof. The landscape, like the students were involved in everything, like the construction of playgrounds there, like building landscape and everything.
Yeah,
Yes.
the time is up.
Yeah.
Thank you.
So
Thank you,
we can
Apu.
Oh, yeah. Sorry. Yeah. Thank you so much.
Thank you ever so much. Just while we're loading the next one, I'm just going to go through the scorecard. Thank you. Shazia, hi Shazia. Are you?
Hello.
Are you managing? Are you able to share your presentation?
Yes, I will share it now.
Thank you very much.
Can you hear me well?
Very well, thank you.
Okay. 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 Good afternoon, everybody. I'm Shazia Dixon, and I have just completed my master's in low energy building services engineering course at Loughborough University. And my master's dissertation was on ventilation effectiveness in schools in the UK. And so kids' right to fresh air. We spend around 90% of our time indoors, and school-age children spend almost 12% of their life in school buildings. Their exposure to polluted, stale indoor air on their developing young lungs can have lifelong chronic health conditions. And damaging effect of polluted air on human health has been acknowledged as far back as the Greek and Roman civilizations centuries ago in crowded cities. And in 1800s, the very well-known German scientist has recommended CO2 concentration levels in the classrooms to be around 700 ppm, parts per million. And it recommended it should not exceed 1000 ppm. And Florence Nightingale also has acknowledged the polluted indoor air in crowded classrooms and suggested that the classrooms were the epicenter of pandemics and parents should not really send their children into such environments to school. And in the UK, the classrooms are, over the years, has become overcrowded. And today, currently, occupancy density recommended for classroom is 1.8 square meter per person. And this is compared to 4 square meter in the US and around 10 square meter per person in an office for an adult. And it is just kind of acknowledging the Florence Nightingale's overcrowded classrooms in the UK. So what are the implications of these? So over the years, buildings became much more airtight. Unfortunately, this concept of building tight and ventilating right has not been realized. And this is resulting in classrooms overheating, children passing out, and children resulting in increased cases of asthma. UK children has got the highest number of cases of asthma in children, according to World Health Organization. As well as asthma, there is also, it affects children's impaired cognitive ability, gives headaches and restlessness. One of the leading earlier architecture of school buildings has described restlessness, inattention, apparent stupidity, often observable among children is not due to teachers' dullness of their subject, but is lack of ventilation. And the chart on the right-hand side is taken during April. It was during still pandemic, from a classroom in the UK. Is showing around 3,000 ppm is being reached at a steady state concentration level. So, and we just assumed this data was not used for my research, but this data shows that we assumed there was no ventilation at all in this classroom, although there was a lot of potential to be achieved. So what is the answer? I have run 12 different simulations, experimented with 12 different strategies. What we are saying is at a global commitment to net zero energy buildings, while we are trying to make the buildings net zero, at the same time, we're also suggesting that blowing the buildings as much as fresh air as possible, it just kind of does not add up. And there will be huge implications of energy consumption. So what we are suggesting is, instead of just blowing the buildings with loads of fresh air, thinking about the ventilation effectiveness. Is the space can be really effectively ventilated? Where the air is needed near the breathing zone, is it reached to the occupants in the space? So these three winning strategies, I'm only sharing the three with you. And the ones showing basically are in blue, they are different where the windows are open. So we are seeing all three were cross-ventilated spaces, and lower and higher openings has been experimented. One of them representing internal and external wall on each part. So as you can see, on a summer condition, 580 ppm was achieved compared to 1300 ppm in winter. And then 600 ppm again, 1300 ppm in winter, and then 600 ppm again, 1300 ppm on the third one. On the third one, we saved around 21% energy. This is heating energy during winter conditions, and compared to the base case scenario in the actual school in the UK. As you can see, the one in the middle is resulted in 5% extra energy usage, while on the first one on the left is the 7% energy reduction was achieved. So this is what we are suggesting. Basically, instead of just ventilating the building as much as fresh air possible, think about the ventilation effectiveness, how it can be achieved with much lower ventilation rate. Thank you very much.
Thank you very much, Shazia.
You're welcome.
Okay. So we've just swapped those around. So we should be Jordan Gilbert next, I believe. Is that right, Joshua? Achieving zero carbon through an integration of architecture and engineering.
Yeah. Is Jordan here?
Hello, Jordan. Are you there?
No, I can't find him in the list.
Ah, oh dear. Okay. Well, perhaps if he's dropped out and he comes back in, if we can juggle things around a little bit, assuming that the presenters are okay with that. In which case, if we move on to Zain Abidi. Hi, Zain.
Hello.
Thank you ever so much. So we'll check the time. Thanks for your presentation. Zain is developing control strategies for zero energy buildings using IoT sensors. So we'll hand over to you now. Thanks ever so much.
Yep, thank you. I'll just.
Darren, we got Jose, one of the judges from Peak Everard here as well.
Oh, thank you. Jose, how are you doing?
Hello, good afternoon. Hello, everybody. All good, yes. I think I probably I got half of the first presentation, but it was good enough to get a good impression of it.
Thank you. Brilliant. Thanks for joining us.
No problem. Thank you to you.
Hello. Yeah, I hope you can see my screen.
No, not yet.
1 second. No, it's okay.
Yeah, it's not full screen. We can see the sort of the different slides to the left at the moment.
Now you can see the full screen.
Yeah.
Right. So good afternoon, everyone. My research topic is developing control strategy for zero energy buildings with improved thermal comfort for using the IoT sensors. But before starting this my topic, I'd just like everyone to imagine a child who goes to a classroom and tries to study and sits in a place. But what happens is that while the rest of the class is able to concentrate and study more on their studies, but this kid is not able to concentrate. Maybe because he's not feeling comfortable at where he sits. Maybe the temperature is high, maybe the CO2 is high. And because of that, he's feeling dizziness, he's feeling sleepy. So that was the idea behind my research topic. That's why I selected this research. And this was not a thing of past. And it's during a very recent research, they have found that which was conducted in 64 schools across 5 Central European countries, that hardly 20% of these 64 schools were able to meet the demand of 1,000 ppm, which is very, very less, and it has to be corrected in every way possible. But while doing this, we have to think about energy also. We have to save as much as possible energy in how much we consume in our buildings. So how to solve these things? How to solve these two problems inside a building? I utilized a technology which is it's a coming up thing, and it's the thing of the future now. It's hardware light. It's a wireless technology. It's not an OEM centric kind of a thing where we have to follow only one company, which is capable. Any company can follow it. So this is which we can use it to solve the problem of schools or of offices. So it's a thing which we can use to improve indoor air climate and to see what's going on inside a classroom, inside an office. So what's the methodology which I used? What I did is that I got an opportunity to work inside a research hub, and I placed 4 sensors in that hall in one of the building in our universities. This is not an IoT sensor, but this is what I've got. This is an HOBO sensor. It's a temperature and CO2 sensor, through which I recorded temperature and CO2. And as you can see in the photo over here, that I placed my CO2 sensor on the table to get the temperature and CO2 readings. So actually, what kind of environment a person is having in that particular area. So that was an important thing for me to note. And to support this, I made an ISV model to find out more about that area. And what I did is that I made a control logic to open the windows. I made this control logic because that's what's available in that area, and I think it's best way to prove we can improve the indoor air quality by making some changes in the control logic. So while doing that, I added one more thing, that I did a CFD analysis. I made supply and extract vents as per the actual site conditions for that research hub area. And what I found, the results was quite extraordinary. We can see it over here on the left-hand side. On top, there's a temperature graph and there's a CO2 graph. And on temperature graph, we can see out of 4 sensors, one sensor was recording more around 26 degree, 24 degree every day. And in CO2 graph, just below it, we can see every day in one place, the CO2 is going high. It's not like 1000 ppm, but we have to consider that it's the whole research hub was empty, like there are hardly like 3 or 4 people around there, and it's around 1200 square meters of area. So even that kind of a spike every day is quite extraordinary. And if we see it in like once that all people comes, and then it will be much more than this right now. The next what I did is that I compared the same sensors and with the BMS values. In the top right hand side, we can see the temperature in gray and blue, and BMS value in orange color. And you can see that BMS values are always lower than what's actually happening on the temperature side. Similarly, on the CO2 side, we can see always this on weekday or weekend, the CO2 values are quite going high, and the BMS is not able to find out what's actually happening in that area. So that was a big concern. If we have to think about like students and people who are in the offices, it's a big concern. And through this thing, we have to utilize our control. I have to put our control and then improve our control. I did the dynamic simulation modeling, and I found out the base model is, without using the new control logic, was around 175, which is quite good. But we have to think in our perspective that this is because there are less number of people and there are some assumptions made right now. But once I put the new control logic, we can see in the proposed model it has increased, but it is almost similar to the European Union or the CFD TM46 recommended values. But it's having said that, that's because I've used HFIC. I've not used Apache HFIC. I've used Apache Sim, and there are more number of people in this while I was there in the BMS in the base model. But what we can see in the last corner.
Sorry, Zane, I'm going to have to. We've just gone slightly over time there, just to sort of 5 minutes for everybody. I'm really sorry to cut that short.
Sure. That's the last slide. There you can see that it's all improved.
Thank you ever so much. Thank you. So just making sure for consistency, just giving people 5 minutes. So thank you. Okay. So just to check again. So Jordan Gilbert, is he not with us? Just have a look.
No, he's still not with us.
Okay. So shall we move on to the next presentation, which is Achieving Net Zero in Hot Climate from Lina Al-Safar. Is Lina here?
Hello, yeah, I am. Just give me a second.
Okay, no problem if you just want to get yourself set up. Thank you.
Yeah, I'll just share my screen now. Can you see the screen?
Yeah, it's not quite full screen. It's still on the presenter. Yeah.
Sweet. Okay, am I ready to start?
Just 1 second.
Sure.
Okay, ready when you are.
Sweet, okay. So hi everyone. Today I will be giving a presentation on my undergraduate dissertation, which was titled Assessing the Performance and Feasibility of Low/Zero Carbon Methods to Achieve High Performance Net Zero Energy Buildings using Bahrain as a Case Study. So that is a mouthful. But the premise of my research was looking at a hot climate, which was Bahrain, a country which I lived in, and just assessing whether sustainability is feasible in the country. So for those that don't know, Bahrain is a small island located to the east of Saudi Arabia. And if you've visited any country in the Middle East, you know it's hot there. There's an abundance of sunshine, and their predominant economic driver is oil and gas production. So Bahrain is a really small island, and to be honest, its oil and gas reserves are coming to an end. And because of that, I think it's really important for the country to look at really achieving circular economy and really reaching out to look for different drivers for their economy. And to me, living in the country and seeing how it works, I thought that sustainable buildings is something that is definitely lacking and something that is definitely needed. So since 2016, Bahrain has committed to a lot of national and international standards. However, given this, there is this kind of inertia that's experienced in the country. If you see it, all the things that they've pledged to seem to be kind of performative in a way because their actual progress is lacking. And that's explained by the Yale Environmental Performance Index. They ranked 172 out of 180, and that's quite bad. So what I aimed to do was I looked at the conventional construction methods used in Bahrain, ones that are still ongoing from social housing projects. And I looked at ways that we could improve it, ways that we could go to the government and say, this is all you need to do. This is what the economics of it may be, and see what kind of change we can make. So let me just go forward. So this was the floor plan that I dedicated my work to. It's housing D11 is the type that the country uses as a national standard. So from my research, using the IESV software, I did a building energy modeling for the conventional construction housing, and I looked at ways to optimize it. So from the base case, the total energy consumption was 60.77 megawatt hours, which was corroborated by other research that I had found in my literature review. And you can see, looking at the first graph, that it does peak within the summer months, as you'd expect within a hot climate, because obviously, hot climate, the buildings are not that sustainable, not that insulated. So they really do require a lot of cooling. And looking at the second graph, you can see that of the total conventional housing energy consumption, 71% is dedicated to air conditioning. And that is a lot, which again is corroborated by external research that I had done. So what I did was I looked at a few case studies. One in particular was the Beitna project in Qatar. And that looked at insulating a home using passive methods, passive house standards, to make it net zero. So by using the materials from that case study, however, tweaking them a bit so that it was resourceful in Bahrain, you can see that there's a major drop, looking at the third graph, a major drop between the base case and the new optimized materials, achieving a really, really low or a really great energy drop. And then what I looked to do was other ways to make it net zero. So that did not make it net zero. As you can see, there is still that amount between the base case and achieving zero. So I looked at wind energy, PV energy, and CHPs. So CHPs, cooling, combined heating and power. I'm sorry about that. Combined heating and power for the building, it had a very high initial investment and initial cost. However, it achieved absolutely nothing for the house. So I left that out. However, I do recommend that cooling, combined heating and cooling may be plausible for Bahrain. However, I wasn't able to test that on the software that I used. And combining everything in all, I was able to achieve a reduction of 103.8%, bringing the building to net positive at negative 2.8% megawatt hours, sorry. And then as you can see, so PV panels did achieve the majority of the energy to meet the demand for the building. However, still in peak summer months, there was that discrepancy between the reduced value from the base case and what was required. So they were still reliant on the grid.
Thank you, Lena. We're at the 5-minute mark, but thank you ever so much.
Okay, thank you so much.
I hope I'm not being tough on people here. I was told everyone's got 5 minutes, so I guess that's.
Yeah, no, I absolutely, I get it.
Not to be the bad guy. Thank you ever so much. Just as we get the next person ready, we'll just, if judges just want to put their scores.
Can I just ask a quick question on the scoring? Does it have to be a whole number? As it does it have to be 1 to 5, or can it be 3.5?
Yeah, you can put decimals. That's fine.
Okay, thank you.
Yes, please give generously.
Okay then.
I don't know why.
Okay. We're ready for the next presentation. So the next presentation is from Hoi-Ching Catherine Young.
Hi.
And I see your presentation is on the potentials of adaptive integrated PMV model for comfort assessment in free running buildings.
Yeah.
So if you're all set up and ready to go, we are ready when you are.
Yeah. Hi, I'm Catherine. My topic today is potential of adaptive integrated PMV model for comfort assessment in free running building. A little bit background on why we do this and the knowledge gap. There are currently two commonly used thermal comfort assessment model. One is Fengus PMV model and adaptive model. Fengus model look at human body balance where we should feel neutral when heat loss equal to heat gain. So without going into details, there are 6 input parameters of the equation. Due to the equation defined in a control chamber, like people cannot change their garments or open window, is more suitable in an assessment of mechanically ventilated building. And in later days, people found that in natural ventilated building, we will adapt psychologically, physiologically, and behaviorally, saying taking on and off clothes. They develop an adaptive model through analysis of past field survey data. The equation adopted in ASHRAE 55th and EN 15251 is not the same, but quite similar. However, there are criticisms that adaptive model is obtained in backboard approach, not a rational model like the PMV, and didn't show the actual adaptive mechanism while neglecting other environmental parameters like relative humidity. So it raises the question whether we can capture the merit of Fengus model while taking account of human adaptation in free running environment, and how can we do that? So basically, we can change the clothing and metabolic rates dynamically to represent the behavioral adaptation in the space. So we conduct a building simulation using Design Builder with Energy Plus from May to September. The building is a natural ventilated building with window control by temperature set point. And we construct 2 models, base model and enhanced model. Base model use typical cloth value and metabolic rates, and the enhanced one consists of 3 cases. One is adjust clothing, adjust metabolic rate, and combination of both. The adjustment is done on a weekly basis, so you calculate the new value for each timestamp and then take average in terms of week. For clothing, it changed based on a behavioral equation developed in
previous study, as you can see. And for metabolic rate, it's changed due to people changing posture or being more active or sedate. So it is adjusted according to some hypothetic condition. And the table on the right show the new value for each week. So after we do all of these, there are two major findings. For base model, it's confirmed that disparity exists between prediction of PMV and adaptive model. So PMV is the most stringent standard, which makes sense because people cannot do things to restore comfort and they probably have a narrower acceptable range of temperature. So it consolidates the fact that PMV is not suitable for assessment of natural ventilated building. Secondly, in enhanced model, after adjustment, PMV model improved by 6%, meaning less discomfort hours. A combined adjustment provides the optimum enhancement as much as 10% more comfort. So the result is promising and leaning to a prediction of adaptive model. This indicates a strong potential of implementing adaptation concept in existing PMV model. And after we have the finding, we have multiple discussion. First, although the equation of ASHRAE and EN standard one is quite similar for adaptive model, their prediction is very different. It's due to the fact that they have different methodology in calculating average outdoor temperature. ASHRAE 1 is a monthly average, where EN is a weekly average with higher impact rating on the day closer to the day. So the problem arises when it comes to May. The monthly approach takes account of a lot of temperature in April, which is a cold month. It creates more discomfort due to coldness, and also since it's considered a large part of April in the beginning of May, the outdoor temperature becomes lower than the applicable limit of the equation, so making a lot of time cannot be considered. So the comparison between the two standards is an interesting thing we can think about in the future. So as we said, the proposed PMV model has a strong potential, but is it enough? Studies have shown that ASHRAE 55th adaptive model, their acceptable band is only suitable for medium humidity. So now we have PMV model which consider relative humidity and wind velocity. With the incorporation with adaptive concept, it's possible to serve as alternative assessment method for country with extreme humidity or wind velocity. And the current time interval set a week is too wide. It's caused scenario of contradicting adjustments. Say this week has 4 hot days, so by taking average, the cold value should decrease. But Monday could be very cold, and the adjust value is just not right for that. For example, in office after adjustment of clothing, there are 26.5 hours change from comfort to discomfort. And the study approach can actually further implicate in mixed mode building, because in mixed mode building, studies show that their comfort and adaptation level is somewhere between PMV and adaptive model. So it's possible that instead of incorporating the current behavioral equation to change the cloth and metabolic rate, we can apply other behavioral models which are derived tailored for mixed mode building. So the final recommendation is that we need to have a shorter time interval, say sub-daily, and we can do that by Python program calculation. Through that, we can have more flexible adjustment and also establishment of more realistic building. And like all of the study, we need a larger sample size in different location and year. And most importantly, we have to have future field study to compare the actual sensation to prove this work. That's the end of my presentation.
Thank you. Just across the line. Thank you ever so much. That was great.
Thank you.
Thank you very much. Okay, so I have Paul David next. Hi, Paul. I see you're getting set up there, so that's great. You just want to get your slides ready.
Yeah. Yeah, hope you can see my screen.
It's just loading now.
Yeah. So, good afternoon, everyone. My research topic is about modeling and evaluating thermal comfort and indoor air quality performance of an office building. Global warming and the need to decarbonize the urban environment are pushing the technical creativity by supplying inhabitants with thermal comfort. But the 2019 pandemic has shown us the importance of indoor air quality inside the building. The quality of air inside the building determines the health and well-being of the people. The indoor air quality has deteriorated as a result of energy conservation, reducing cooling, introduction of new materials, and various other sources of indoor air pollutants. So it is important to maintain the indoor air quality. Understanding and managing common contaminants in the indoor air can help minimize your risk of health issues. The research developed a control strategy to improve the indoor air quality and thermal comfort without much increase in energy consumption. Design Builder Energy Plus is used to simulate the building and to simulate the temperature and energy of the building. And Quantum Indoor Air Quality and Ventilation Analysis software is used to simulate the CO2 and TVOC contaminants of the building. Model of the building is developed and simulated to find the best possible control strategy to create good indoor air quality with low energy expenditure. Temperature data and contaminant data such as CO2 and TVOC of the building are measured using IoT sensor, and the figures are collected from building management system. The measured temperature and contaminants is compared with the data collected simulated using Design Builder and Quantum software, and the results are discussed. The building model is simulated for Scotland weather, considering an occupancy of 6% each zone, and 8 different cases are carried out. Contaminants such as CO2 and TVOC are simulated for each case in Quantum simulation software. These exhaust fans and pressure fans are run at different air change rates, and the contaminant values are simulated. The temperature and energy simulation is done using Design Builder Energy Plus. To find the hourly temperature at different locations of the building, virtual partitions are created in Design Builder, which are present virtually but not really. This helps to find out the exact location, the temperature at the exact location of the sensors. Both CO2 and TVOC contaminants decrease for increase in air change rate. Addition of exhaust fans to the base case reduce the contaminants concentration in the zone. The exhaust fans operated at 1.5 air change rate is more effective than the exhaust fans operated at 0.5 and 1 air change rate. There is no much difference in contaminant values at the exhaust fan operation of air change rate at 1 and 1.5, but the energy consumption of the building with the exhaust fan at 1.5 air change rate is much more than 1 air change rate. As there is only slight difference in contaminant reduction between exhaust fans operated at 1 and 1.5 air change rates. Exhaust fans with 1 air change rate is used, which uses less energy than the one operated at 1.5. This optimal case with the exhaust fan at 1 air change rate is then added with the pressure fan at 3 different air change rates to find the optimal one. It is found that installation of pressure fan along with the exhaust fan further reduce the contaminant level in the building. The pressure fan, when operated at 1.5, removed more contaminants than the one operated at 1 air change rate, but the energy consumption of the fans at 1.5 air change rate is more. So ideally, both pressure and exhaust fan at 1 air change rate is used to remove the contaminant level. The energy consumption of the building is quite high than the base case. Therefore, it is proved that for reducing the contaminant level, the energy consumption will always increase. Another case is of using Windows operation or automatic window operation, which removes more contaminants than the other cases. But the main drawback is that it affects the thermal comfort inside the building. A reduction in the thermal comfort will increase the energy consumption of the building. Therefore, installation of exhaust and pressure fans at 1 air change rate is proved to be ideal case for contaminant reduction, considering temperature variation and energy consumption. The results showed that reducing contaminants will definitely have energy consumption, increase in energy consumption, which is similar for all the cases. Finally, the study concludes that the contaminant reduction is more effective when pressure fans and exhaust fans are operated at 1 air change rate without having much impact on the energy level and temperature comfort of the building. Thank you.
Thank you very much. Thank you, Paul. Okay, well, first of all, thank you very much to all the students and for the presentations. See lots of work gone into that, and appreciate it can be quite nerving when you're trying to do these things online as well, overcoming any kind of IT problems. So thank you again. We're going to take a short break for 10 minutes.
Darren, we have one more presentation. Gary Parker.
Oh.
From De Montfort.
Sorry, my apologies. Yeah.
Yeah.
Changed the sheet just recently, and I'm looking at the older one, so my apologies. Okay, is Gary here and able to bring his slides up? Great.
Yeah.
Sorry, Gary, nearly left you out there.
That's all right. I've got the graveyard shift there. Just everyone's desperate to go for a break now. Let me see if I can share.
Yeah, I say you've got plenty of time, but it's 5 minutes, but you've got plenty of time. But once you're up and ready.
Yeah, no bother. You just say when.
Thank you. Yeah, thanks, Joshua, for the prompt there. Okay, yeah, ready when you are.
Thank you. Afternoon, everybody. My name is Gary Parker, and I work for a company called the Electrical Contractors Association. And I empathise with a chap at the beginning who said about his mother forced him to get a job in an apprenticeship sense. I did something similar, unfortunately, a lot more years ago than I care to recall now. I originally trained as an electrician, and over the time, be it for personal, professional, or educational reasons, I've become more interested in the green economy and the future and training of organisations and individuals. And recently, as part of my MSc at De Montfort, I've been looking at training, qualifications, education with regard to the green economy. And the things like the UK engineering sector has over 60,000 firms and 350,000 individual professionals working in them. And historically, designers, engineers, installers, apprentices have always trained in the same way. We've looked at the same things. We've considered the same things from an electrical installation point of view. Sockets and lights predominantly make up the large part of our installation. We've got some things like data. We have some things like fire alarms. But contractors have trained and engineered the same solutions for many years. And in 2019, a TESP report, the Electrical Skills Partnership, suggested that we might need another 12,500 to 15,000 additional skilled professionals in the next 5 years. And this report was based pre-COVID and pre a green revolution, a green economy. And my dissertation, my project, my work is, are these practices, is what we're doing now right for us and also right for the future? Future technologies, new systems, new engineering practices, renewable energy systems, things like electric vehicles, storage systems, battery energy storage systems, electrification of heat, and the electrified society is something that is going to increase. The UK government has been the first major economy to pass net zero 2050 rules, and organisations like the UK Solar Energy have reported that the industry will need an additional 13,000 new employees to generate 40 gigawatt of solar energy, which is part of the targets for the UK. ECA, the Electrical Contractors Association, is part of a European group of associations, Europon. And Europon, a recent study has suggested that we're going to have an extra 383,000 individuals in the engineering sector by 2030. A recent Skills for Climate report highlighted that 88% of businesses support a green economy. So there's a real push for green economy, green growth, green institutions. But this is great, but presents challenges, not just to myself, not just to my children, but to the industry as well. There's simply not enough people to do the work. There simply isn't enough out there. A new generation is more aware of energy, climate change, and the green recovery. But currently, we have an aging workforce, particularly in the electrotechnical sector, with far, far too few entries into that sector. There are too much tax on energy efficient products, not enough subsidies on the technologies for people to fit. Following a recent energy efficiency audit in one of the buildings that my employer owns, almost none of the suggestions were feasible, practicable, or potentially useful. Existing systems that separate industries and trades, we see a plumber is a plumber, we see an electrical person is an electrical person. They don't mix. Yet one of the other delegates mentioned combined heating and power. We've got air source heat pumps that are a combined system. We need some form of upskilling, some collaboration, and this is the only way we can generate enough work and enough people to do this. And even in terms of training and education centres, universities are great places for education, but a lot of the hands-on knuckle scratching contractors out there don't attend a university. They attend a training centre, a small tech college. They don't have the staff. Those staff aren't trained to deliver the battery energy storage type courses. ASHRAE UK is an alliance representing the multi-billion pound UK engineering sector. They've recently launched a manifesto which highlights these problems and a few others with the green economy and the green recovery. So my presentation today, rather briefly, unlike some of the others where they've been incredibly technical, was more of an overview of my studies at De Montfort. I'm not asking whether we should do a green recovery and look at a green economy, but whether we can deliver it. And at the moment, it doesn't appear that we can. We need to change what we do. We need to look at upskilling, and we need to get more people into the engineering sector. And my studies are showing that we haven't got that yet. That's a personal thing as well as a professional thing as well from my employer as well. And that's a very short overview of what I'd like to talk about. Thank you very much. We can go to break now.
Thank you, Gary. That was I just got that across the line on time, and thank you ever so much. That was very interesting. Yeah, sorry to almost cut you short there. So we will take a brief break now for 10 minutes. So it's coming up for 1:45. I'll just check the time. Yeah, so we'll reconvene in 10 minutes time. In which case then we'll proceed with the PhD presentations as well. Just quickly, actually, before we do break, Jordan Gilbert still is a no-show. Is he not here with us? He's got the opportunity or not to present. Let me just have a look. Speak up, Jordan, or forever hold your peace, I think the saying goes, isn't it? Doesn't appear to be with us, so. Okay, well, thanks again to all the students that presented so far. And let's take a short break and we'll see you in 10 minutes. Thank you. Okay, I think is everybody back? Ah, great. So, we have all the judges back as well.
Yep. Yeah, Darren. Jose here.
Great. Thank you very much.
All good.
Okay, so we're going to move on to the PhD presentations next, and the first presentation is the impact assessment of architects' knowledge repertoire on energy efficient building, and is Ahmed Al-Adawi. Sorry if I'm not pronouncing this correctly. Just to remind all the presenters there, so you have 5 minutes, so per slide. So once you're set up and you're happy, we'll start the 5 minutes from once the slide's up there and everything's good.
I think Sid is not here. No, he's not here.
Okay. Shall mark down. Do we have Ahmed Al-Adawi?
Yes, I'm here.
Nice to see you. Okay, Ahmed, if you'd like to bring your slides, slide deck onto the screen.
Okay, I'll share it later during my presentation, if you don't mind.
Absolutely, absolutely. Just let me know when you are ready to go, and we shall start the clock.
Yep, I'm ready.
Okay.
So, hello and good afternoon, everyone. My name is Ahmed Al-Adawi. I'm a PhD researcher at Gilbert University. I have a computer science background and a distinction master's degree in Internet of Things, which Zaid Abidi has just explained what is IoT. My research is indoor environment design for a dementia-friendly home using smart IoT technologies. I'll start with the current pandemic, COVID-19 pandemic, which has its impact on everyone's life. The most recent one is this competition was being held online. However, there's another pandemic which has no vaccination program, which is not covered yet by the media as the current pandemic did, which is dementia. So people with dementia, recent studies have confirmed that people with dementia have different thermal levels and expectations than the normal people, which makes designing an indoor environment for people with dementia and their caregivers such a growing challenge. So people with dementia, most of people with dementia spend 90% of their time indoors doing different sorts of activities. And I believe each activity has its own comfort settings. Activities such as sleeping, such as watching TV, or even exercising on the couch. Now I'll share my presentation. Please confirm if you can see it. Yeah.
Yes.
All right. So, indoor environmental design for a dementia-friendly home using smart IoT technologies. To achieve this optimal indoor environment, I'm proposing a smart control system. A smart control system that firstly identify the activity that the patient is doing indoor and activate the comfort settings attached with the identified activity. Let me start with right in the beginning of this flowchart. So firstly, we're gonna take the IAQ readings and match these readings with the time, the dynamic time and the place to locate the patient and to predict which ADL or activity of daily living is the patient's doing in the real time. Initially, I'm including 4 main activities in the system, which are sleeping, cooking, exercising, and showering. Of course, more activities can be included, but for the sake of simplicity, I'm just including these 4. After predicting the ADL, we will activate the settings or the comfort settings attached with the predicted ADL. And if the patient or the caregivers has changed these comfort settings, it will be reported and the system owner will be identified. In this case, the caregiver. Let me give you a small demo of the proposed system. So I have programmed the system. If I just play this video. So first we're going to take the temperature, let's say 20 degree, relative humidity, let's say it's 50%, CO2 level indoor, let's say 500 or 600 ppm, and the airspeed is 0.2 meter per second. After taking these readings and the dynamic time, it will predict the activity. We know that the activity of daily living setting is deactivated because we haven't predicted the activity yet. If we predicted it, it will give us the patient name and the activity is being taken, which I'm presenting now in the ASHRAE competition, and whether it's confirmed by the caregiver or not. Once the predicted ADL is predicted, we can activate the settings, in this case, turning on the TVs, opening up the window, turning on the fan, and so on and so forth. By achieving this control system, so this system will be installed and tested in 2 different dementia-friendly homes to not only provide the optimal indoor environment for people with dementia or their caregivers, not only to reduce the cost of dementia cares in the UK, which is reaching nearly £30 billion by 2025, but to be a small step in engaging people with dementia in the society, make them more independent, and somehow giving them back what they have lost. Thank you for your time.
Thank you very much.
Thank you.
Okay, so we're going to move on to the next one now, which is investigating the impact of water quality in reducing the performance of closed-loop heating and cooling systems, presented by PhD student Amir Suleiman. So once you've got your slides ready, Amir. Thank you.
Darren, Amir's muted.
Okay, could you hear me now?
Yes.
Okay, I think it mutes me automatically. Are you able to see my poster now?
Yep.
Fantastic. Yeah. Brilliant. Okay, I'm ready to start now.
Okay.
Good afternoon, everyone. And I'll be presenting about the impact of water quality in closed-loop heating and cooling systems. I'll present it in the form of a poster so you'll be able to listen to me rather than reading a lot of stuff on the screen. The reason why we're looking at water quality is because water quality tends to be the catalyst for a lot of the issues that lead to degradation of heating and cooling systems. And it's quite something that is novel, that has not really been investigated quite a lot. So for example, water has a lot of dissolved gases. Dissolved gases like dissolved oxygen leads to corrosion, and corrosion leads to plant failure. Dissolved minerals leads to scaling. Microbiological activity leads to corrosion. At the end of the day, all of these lead to severe energy losses, plant failures, which in turn leads to a lot of cost. For example, the World Corrosion Authority found that in 1 year, the corrosion losses in the UK, corrosion could cause economic losses north of £3 billion. So it's quite something big that we need to consider. The methodology for this research, number one, is we've developed a state-of-the-art experimental rig that allows us to replicate a typical closed-loop heating and cooling systems, as you can see over here. With the rig, we're able to install different types of mechanical filtration. We install the conventional dirt and air separator or an inline filtration system, and we've installed an innovative side stream filtration system, which allows us to compare how they are able to restore system efficiency and improve system efficiency and improve the water quality. The second step, because of the heterogeneity nature of the data and the volatility of the data, we are going to apply a machine learning model that's able to make relation between these hidden parameters. As I'll go through later, there's a lot of parameters, and the way they are linked to each other is quite complicated. That's why we're going to use a machine learning model to be able to come up with more thorough and better conclusions. The final step is we're going to incorporate building information modeling. We're going to do this by incorporating a virtual reality model. So we're going to develop the rig or the plant that we are studying by Revit, and then we're going to use the outputs from the machine learning model and combine it using a gaming platform, which will be visualized by them. This is important because the nature of research is you need to be in touch with the daily users, the engineers, the homeowners. So that step is to make us connect with the people who are going to be using, hopefully, this project. If we go through the results, just to give you a quick summary of results. The first one shows the mechanical filtration and the impact of reducing dissolved oxygen. As I said, dissolved oxygen was the igniter of the galvanic corrosion. And generally, when we install mechanical filtration, it's quite effective in reducing it, as you could see from the first figure. Chemical inhibitors. We've also looked at that as well. Chemical inhibitors, they were able to reduce the time by about a third, roughly 53% quicker. However, this is when we saw some issues. So the temperature, when we did both exercises, the temperatures was quite high. So for the with the inhibitor, it was during the week where we had quite a heat wave. So the temperature was 10 degrees higher than it wasn't. And we saw the dissolved oxygen fall more rapidly. So and this was validated by Henry's law of solubility, where the increase in temperature reduced the amount of gas in the liquid. The final one is the conductivity. As I mentioned, chemical inhibitor was quite good in reducing the dissolved oxygen. However, it increased the conductivity by around 1,000 microsiemens, when normal water is 500 microsiemens. So as you can see, as the conductivity increases, the dissolved oxygen decreases. So this is another relationship. The German directives, VDI 2035, states that conductivity needs to be below 10 microsiemens. And if that's below 10 microsiemens, then then corrosion is going to be limited. As you can see, there's a lot of different factors that goes into this, and also there's no defined guidance on how we could tackle corrosion and improve water quality. And this is the base of this research, to try and shed more light into this topic. Thank you very much.
Thank you.
Good.
Okay. If the other judges are completed as well, ready for the next presentation. So the next presentation that we're showing is monitor and optimize office buildings using distributed sensors and intelligent controls by Joshua Vasudevan. So Joshua, if you're ready, the floor is yours.
Yeah, thank you, Darren. Hi, everyone. So I'm Joshua. I'm doing my PhD at Loughborough University. My topic is monitor and optimize indoor air quality in office spaces using distributed sensors and intelligent control. So as you have seen so far in the presentation, there has been a lot of emphasis on indoor air quality. So over there has been a lot of research conducted in the indoor air quality, thermal comfort, and energy field. Most looked into the pollutant concentration and evaluation of evaluation of indoor air quality in the buildings. So there has been like less emphasis on indoor air quality and control field. So this COVID has already taught us that how it is important to control the IAQ in the buildings. So, and also the emerge of AI technologies have shown us what data can do and its power. So this research focuses on the importance of data and then machine learning algorithms, which can use to control the buildings automatically so that you will feel comfortable as well as you'll have good indoor air quality without any compromise on energy. So in this research, like I did a literature search. So for the controls, there are like 3 types of controls. One is traditional control, one is predictive, and there is intelligent control. So if you see the traditional control, it's the rule-based and PID controls. And for the predictive control, that's the model predictive control. And for intelligent control, we have the neural networks and reinforcement learning and other machine learning techniques. So the pros of traditional control is it's easy to implement, and the cons are like slow and inefficient most of the time. And the predictive control, it's highly efficient, but it's hard to implement, and also it's very complex. For the intelligent control, the pros are highly efficient, but the cons are we need more data, except for reinforcement learning, because reinforcement learning is something which learns itself without any data. So this is what reinforcement learning will do. So we have the environment, and it takes the observations from the environment, and it has an agent which gives the action back to do, and it says like what it has to do. And once the actions are done, it will again see the observation, and it will give it a reward. So for each action you take, it will give you a reward. So if it takes a wrong step, the algorithm will receive a negative reward, and if it takes a right step, it will receive a positive reward. The rewards are based on the constraints we set. So if we set the constraint as indoor air quality, thermal comfort, and energy, then obviously whatever constraints we set, it will automatically learn and get the reward. So it learns based on the rewards that it gets. So this is the case study building that I have. It's an office space. So what I'm doing is I'm measuring temperature, relative humidity, CO2, and TOC on each workstations at different places, so that I can, understand the indoor environment situation at each space, so that I don't leave out any space in the, in the office. And also, I will collect occupants' feedback for thermal comfort and indoor air quality. So I conducted an initial pilot study to look into the IEQ of the space. It looks like, there isn't a good distribution of temperatures in the space. You can see the sensors reading here, and for each day for the working hours. So you can see sometimes there isn't like good distribution of temperatures between the space, like there is like around sometimes it's around like 4 degrees changes between each, in the same space. It's like 21 here, and it's like 25 in this end. It's like kind of a lot of differences in the temperatures. And also, if you see the CO2 and TVOC level, it's going beyond the limits. So sometimes when the meeting rooms are occupied, it's just boost up during that time, and it's not reducing because there isn't proper control in that space. So this clearly indicates that there is a need for an optimal control in the space. So the proposed methodology is like I will try to capture all the parameters like the indoor environmental parameters like the temperature, relative humidity, lux level, CO2, TVOC, and then I will capture the occupants' sensations based on their votes, and then I will have the smart watches through which I can, like Fitbit, I can monitor their O2 oxygen levels and other heartbeats and other parameters through that. So we'll record all those and we will be adding it to the database, and also I will take the weather conditions and I will add it to the database through which I can create an ML model. So the machine learning model will get all these things and it will learn what is the situation, how is the occupant feeling, and it will create a model of that space, which I will in turn optimize and control and optimize using my reinforcement learning. So the agent will automatically start to learn what is there and it will automatically control the space. So this is the network, and it will send the control signals to the main controller through which it will control the space. And also we can have it as a visualization where we can send weekly feedbacks to the spaces, to the occupants in the office spaces, and say them, okay, this is the situation at each point of the space. So, and based on the control, how much we are efficiently controlling each space. So this is the proposal, and further work needs to be done on this side, where I need to create the ML model and then do oral to optimize the space.
Sorry to cut you short there. I realised to run a bit over time there. So thank you ever so much. I think I do believe that concludes all of our presentations. I believe we've had some, unfortunately, that couldn't make it. So I think, first of all, a big round of applause to all the students for the work and effort that they've gone into their presentations. They've all been absolutely fantastic. So I'd just like to give everyone a round of applause. Brilliant work. So we will be taking a look at the results from the judges, but in that time, whilst we do that, we are very honoured to have a distinguished lecturer join us today, Frank Mills. So Frank, are you there?
Yes, I am. I'm here. Yep.
Oh, fantastic. Frank, would you like just to introduce yourself to the, I guess, the audience? And,
yeah, sure.
Yeah. Talk about. Thank you.
Okay, can I put my slides up now? I've got some slides to go through, and my title's on there. Okay, open share tree. Open share tray. Okay. Choose what to share. Entire screen. Right. Do
we need to give you control, or?
Don't know. I can see it on mine. Can you see that slide now?
Yes.
On yours?
Yeah. Perfect.
Right.
Yep.
Good.
Thank you.
All right. Okay, everybody. I'm Frank Mills. I'm an ASHRAE distinguished lecturer. So I think I've got about 35 minutes. Is that right, Darren? Or whenever you allow me.
Yeah, giving you, excuse me. Yeah, you've actually got 40 minutes.
Okay, so we can take some questions as we go or at the end. But I wanted to talk about something I've been doing as an ASHRAE distinguished lecturer for the past year, because ASHRAE formed a task force to deal with COVID. And so I was invited to join that. And that's been an excellent experience for me, because we've developed a lot of good information to support engineers all around the world in how to cope with COVID, which of course is a airborne transmission and something ventilation engineers have to deal with. So just to let you know, when we do an ASHRAE topic like this, we have a formality we go through. The slides are approved and ASHRAE kind of own it. And this one I put together here, I'm acknowledging some of the other people from the task force. I've got some names on here. So you can circulate these slides later if you want, Darren, but it's just an example of how we do these presentations. And then what I've really wanted to say right at the beginning is that if you go to the ASHRAE website and look at ashrae.org/COVID-19, you will find an infographics page, which is a starter page, which will get you into all sorts of sectors like healthcare, schools, daycare centres, shopping, all of those different building sectors. And each of those has information on how to reduce the risk of COVID transmission between people, keeping people healthy, safe and well, using engineering solutions. And I estimate there's more than 500 pages there. So it's been a lot of work with a lot of people, of course. So I've been privileged to have been part of that. So I just wanted to run through quickly some of the things we found that we can use as engineers to reduce COVID risk and reduce the transmission and get back to some kind of normality. And I wanted to also say that we had this idea of being infection control engineers, and many of us think of ourselves as building services engineers, which we are, of course, but in this area we're really helping to control infection using the various techniques at our disposal. And to do that, we need to understand something about the virus we're dealing with, in this case COVID, but there are other viruses and bacteria out there which we want to take out of the air and cut its transmission routes from people to people. We need to know what the solutions are that work, and in doing that, we're trying to protect people and the spaces they're in. And as engineers, we want to go down and do things. We go to sites, we'll check things, we'll make investigations, identify problems, find a solution, and then we'll make sure that the solution we put in actually works. So just to tell you very briefly something about coronaviruses, they're a single-stranded RNA virus, that's nucleic acid virus, and they've been with us for a long time. So we all know about the common cold. Most of us have had the cold at some stage or other. And we all know about SARS-1 when that came along, and MERS, and these abbreviations for South Asia Respiratory Syndrome and the Middle East Respiratory Syndrome, MERS. And here we have SARS-2. So it's a South Asian Respiratory Syndrome number 2, but it's been called COVID-19 because it appeared in the end of 2019. And that's, of course, the pandemic around the world, which is worrying us all at the moment. I'm not going to go into this in great detail, but I found it fascinating to try and understand myself what exactly SARS-CoV-2 is. And so if you look at the reference at the top on the page and you go and look at that paper, it's about 8 pages long, but it explains exactly what it is and how it affects people. And essentially, it comes along in those little green and brown circles at the top, and it comes into the human body, and it wants to get into human cells. So that lilac or purple line you can see there going from left to right, that's the boundary of a human cell in someone's throat. So these SARS virus come along in the air. It's called them aerosols because they're very small. They're less than 3 micron. They're very, very small indeed. Can't see them, of course. And they come in and they try and latch on to these ACE2 receptors in the human body. When they do, and you can see that one in the middle there has managed to do that, it then enters the cell, the human cell that is, and it has with it its genome, which is its coding really, which says what it is, how it's made up. And with that, it then starts through a process, which I've shown there. Well, sorry, it's not my slide, but it's shown there as number 3, translation. Number 4, proteolysis. 5 is RNA replication. Going to 6, which is transcription and replication of the viral genome. And 7 is viral protein translation. And then finally gets to viral assembly and becomes mature at number 9. And then releases itself again from the cell to outside. But in that process, it's generated a couple of million more of these viruses that go out of the human body by breathing out, coughing out, sneezing, to go and infect other people. So obviously, like any of these things, it's trying to replicate itself, and it's using this human cell to do that. I'm not going to go into any more detail here, but if you look at that paper reference at the top, you'll find an explanation of that process. So virology, very interesting subject. And this essentially is what's happening to us when these cells come towards us, enter the human body, and then they're really trying to replicate and then release and then replicate somewhere else. In terms of size, we need to understand they're actually very small. So the coronavirus there is 120 nanometers. It's tiny. There are some smaller viruses such as Zika virus and hepatitis influenza, and there's some bigger, measles. But we then find they're all below a micron, of course, that we get to bacteria. Bacteria are a bit bigger. Of course, we can't see any of these things, but bacteria are bigger than viruses, and then the bigger things than those would be molds and spores, some of which we can start to see. But these things cling to each other, so they don't tend to float around on their own. They become what's known as a colony-forming unit, and we then have to look at where they are and how we can get them out of the air. So the good thing is we have some of these very big organizations around the world that monitor this stuff all the time. So the CDC, which is a US Center for Disease Control, has really been at the heart of this, releasing quite a lot of information about COVID and other diseases for that matter, but particularly with COVID-19. If you go on their website, which I've shown there is at the bottom, you'll see all sorts of information. And that's been updated through the past year because some of the thinking on this, some of the scientific knowledge has evolved. I was going to use the word change, but I guess it's an evolutionary process. And of course, in particular, there was a strong belief at the beginning that this was transmitted by touch. So people touch surfaces and then put their fingers in their mouth, and that's how COVID got from one person to another. Of course, many of us as ventilation engineers realize that because it's a respiratory disease, it's in the air, so it's transmitted by air. And that is why ASHRAE really stepped up very early on with our task force. That was in March last year we formed, and we started to develop solutions to deal with airborne transmission. But the airborne transmission side wasn't acknowledged by CDC and the World Health Organization until after last summer. But it is now widely acknowledged that COVID is transmitted by air in about 90% of all cases and by surface in about 10%. Obviously, we still get surface transmission because when we speak and we emit droplets and aerosols, they do fall onto surfaces. So COVID does exist on surfaces and people can certainly pick it up that way. You know, if you were on an escalator and you touch the handle of the escalator and the person behind you touches it, you can transmit one to another that way. But the majority would be in the air, and it has always been that case. It just took these scientific people a bit longer to realize that. We've got our UK advice coming through. These people do speak to each other, but they develop their own advice, and there are some differences. So the UK government advice is at the bottom there, and I've put care homes up, but there's a whole range of advice for different people. And more recently, the Royal Academy of Engineering published this report for government in July 2021. So you'll find that available on their site, which is on the right. So CIBSE had an involvement in this, and I was also involved, if you like, as an ASHRAE person. The report is about 8 pages long. Unfortunately, it doesn't really get down to detail, which what I would have liked to have done, although it does direct people onto the ASHRAE website for more information. But what it really does do is talk to government about the fact that we need better engineering, we need engineering solutions, and we need competent, trained engineers. And I think they see a follow-up piece of work to this, which hasn't started yet. But that was only recent, July 2021, where we here in the UK were advising our government that we should be taking engineering solutions into account in order to deal with COVID. And I say that because as a member of the ASHRAE task force, we have been doing that in the United States and elsewhere for at least a year. And what we've been doing is talking about engineering mitigations and in particular ventilation. So if COVID is in the air, there are various things we can do. We can have higher ventilation rates. So if we reduce the peak concentration of the virus or the viral load, then we can remove its effect. In other words, dilute it. It's a dilution effect. So the more air, the less impact that COVID would have. We know that airborne exposure increases with time. With smaller rooms, we have more of a problem. Bigger rooms are better. And of course, then there's the breathing rates, whether people are talking, singing, exercising, shouting. All these things will make a difference to how much aerosols they're emitting from their mouth. Now, one thing I would say at this point, of course, is COVID is only there in the room if somebody who has COVID actually enters the room. If people in the room don't have it, then clearly there's no risk of transmission at all. The problem we have is we don't know who's got COVID, and we don't know when they're going to enter the room that we're in. So we need to have these measures in place to deal with that risk. And finally, of course, if we're outdoors, there's very little risk because outdoor ventilation rates are very high. If you're stood on a mountain, for example, and somebody with COVID approaches you, you're not going to catch COVID off that person because the ventilation rate is just too high for that to have any impact on you. Now, the other thing we can do is clean the air. So we could start trying to inactivate the microorganism. So I would say, as I said in the first point there, that's not a reason to reduce ventilation. We still need fresh air as human beings. So air cleaners don't actually provide fresh air. What they do is clean the air in the room by pulling the air through, and then they either filter it or they deactivate it using UV. And there are other systems which we would not recommend at this point. If you look on the ASHRAE website, we refer to them as emerging technologies. So we're not saying they're not worth thinking about, and they may have certain applications, but we don't think they're really relevant at this point in time. The two relevant solutions are filtration or UV air cleaning. We look at application with recirculation, and we don't recommend recirculation anymore because of the fact that we are possibly recirculating COVID aerosols around the building and spreading it. So we're on to full fresh air, which is unfortunate because that's a high energy bill, unless we can clean the recirculated air using air cleaners. So what we might be able to do is use portable air cleaning units or wall or ceiling mounted. As I say, the two solutions would be filtration. It has to be a high quality filter like HEPA because of the small size of these organisms, or UVC. And as I say, the emerging technologies, and I mentioned air ionization, plasma, chemical cleaning, ozones. Not a lot of data around on those at the moment. We certainly know there's some human side effects, possibly carcinogenic, poisonous, toxic. So we would wish to avoid those. And finally, just consider the other impacts of these devices, such as the flow rate for air in the room, any noise it makes, the fact that it has to be installed and maintained, and you need people to get to those things. And I'll mention that later. And then there is, of course, an operational cost. If you're plugging a device in, a filtration device or a UV air cleaner, it will be using some energy and it will be emitting carbons. Beyond the current pandemic, we think we're going to have to make measures to our buildings to improve health. So it's an interesting fact at the moment that the only buildings here in the UK or elsewhere for that matter that we designed to reduce infection spread are hospitals. So there's no requirement in our building regulations to reduce infections in other buildings like offices. And I'm sure many of you will have worked in an office and seen somebody come in one day with a stinking cold and thinking, gosh, I'm going to catch that if I don't get out of here pretty quickly, or if he doesn't get out. And sure enough, that person could spread a cold all around the office fairly quickly. But we don't actually design systems to stop that happening. I think all that will be changing. That's one of the things that's come up for us to think about. The other aspect to think about at this point in time is reopening buildings, because we've had lots of our big buildings closed now for well over a year. In fact, the Sunday Times this week mentioned that the occupancy rates in London were still only 19%. So 81% of people who work in London are not back at work yet. And that's pretty well repeated around the country. So we've had these big buildings empty for a long time. So we need to have a look, and there's information on the ASHRAE site about getting buildings ready when people come back. CBSE's also published stuff, and I wanted to mention it here because you may or may not be aware that it does get mentioned regularly. I've been involved in this as well because I'm a liaison between CBSE and ASHRAE, and this was the first document we did back in May 2020 on the right-hand side on ventilation. We're now up to version 5, which was published on July the 16th, 2021. So in the past of a year, we've updated that 5 times, and it shows how fast moving this pandemic work has been and how fast we've had to react. I wanted to just remind you about the way microbes get around the building. They're not something we can see very easily, unfortunately, but they're there, and we're all covered in microbes all the time. We are breathing them in and out, of course, and most of them don't do us any harm, or if they do, we've got mechanisms in our body to cope with them. Obviously, with COVID, we haven't. If you breathe in COVID microbes, they're going to make you very ill. So we need to avoid that. That's what all this is about. But it's interesting in the meantime to consider how this does happen. And if you had the ability to look at what's going on in the air, you would see these colony forming units full of all sorts of microbes and viruses, bacteria floating around, and a person in the room touching the surface and being transferred from their hand onto the paper, in this case a drawing. Every time they move, they disturb microbes on the surface there, which come floating back up into the air as aerosols, and then they're also got them on their body, so these microbes are falling off their body all the time. In many cases, they're generated by skin, which we release 3,000 thin skin squams an hour, and they float into the air. And again, they're small colony forming units of multibacteria drifting around unseen. So where people like me thought air was 21% oxygen and 79% nitrogen, it's actually got a lot of other stuff in it that we can't see, and some of that stuff is dangerous. So we've really had to work hard through this pandemic to identify how to remove that as efficiently as possible. Now, of course, ASHRAE has done quite a lot of research on this, and this is Stephanie Taylor's work from Boston. She studied hospital ward areas and nurse stations, and she wanted to know what were the factors in the air that affected people's health, what kind of things led to hospital-acquired infections, and how could we stop them happening. So she looked at temperature, the amount of staff and visitor hand cleaning that went on, whether the room was pressurized positively or negatively, light levels, CO2 levels in the room, relative humidity and absolute humidity, also room traffic, how many people were coming and going into the room, and room air changes, and what kind of outdoor air fraction was part of that. So in the US, it would be common to have maybe 20% fresh air and 80% recirculation air, and that might be 10 air changes an hour in total. So she collected 8 million room data points and found 300 patient outcomes, and from that worked out how we might stop some of these spreads using HVAC systems. So we know that COVID-19 is spread by droplets from the mouth. Larger droplets, which are defined as anything above 10 micron, tend to be on the heavier side, and they will fall downwards within about 3 meters onto surfaces, fall onto clothing, and it can be spread if people touch each other, so hence the need for social distancing. But the smaller droplets, which are less than 10 micron, tend to be almost weightless, so they'll float around in an airstream and can drift a long way. 10 meters or more is quite common. So they can drift from one room into a corridor or into the room next door, so quite a long way. So they're more like a gas, really, and we have to find ways of dealing with those. But don't forget, the larger droplets can also become small as they evaporate off moisture and start floating around. And you can kind of see it in this picture fairly quickly. If you had these different size droplets in the air, ranging from 100 microns down to 0.5 microns, the bigger ones might stay in the air for 6 seconds only and manage to travel maybe a meter, whereas the smaller ones could float around for several days actually, just like a gas might, and be floating 10 meters or more away. So this is also what might happen if someone coughs. You know, when someone coughs, we do get the feeling that there's some dodgy stuff coming our way, but actually it can be quite awful and affect us. In Wuhan, they did do tests on how widely contaminated the COVID virus was, and what they did find, and if you look at this slide on the left, you'll see a bed bay with a corridor outside, and they measured at sites 1, 2, and 3 in that configuration. What they did find, looking on the right, was the rate of positivity was 40.6% in the bed bays on either side, but in the central corridor area where there is no patient and no bed, they were still getting positivity of 12.5%. In other words, there were COVID aerosols traveling out into the corridor and along the building. So we need ventilation systems that can deal with that. So moving on fairly quickly, we do have to consider what happens when we open buildings after a year. And I'm not going into great detail here, but there's an awful lot on the ASHRAE website, which is freely available, by the way. We took the view that we should help the world get over this problem by making all that information available. And what we need is to go back and clean, repair, maintain the systems we've got, check them that they work properly. And that may involve some recommissioning, of course, after a year shutdown, and then take additional steps to prevent any COVID-19 transmission. So we may have a perfectly good ventilation system that we've got up and running again, but we might want to install UV air cleaning or better filtration, or even increase the ventilation flow by moving the fan speed up or changing the fan altogether into a bigger fan. And we want to do some risk assessments, training and behavioral changes so that people appreciate that it's a different situation. So a good example of behavioral change might be lift usage. So the recommendation in the CfD guidance on lifts is we only have one person in a lift at a time, because people need around 36 square feet around them so as not to transmit COVID. So if you get 2 or 3 people in the lift, or a packed lift for that matter, you're going to get a super spreader event once someone with COVID steps in. So the behavioural change might be to say, well, you've got to wait for the lift longer. Now, the contrary to that would be to say, well, can we, as ventilation engineers, find some way of cleaning the lift air? If we put a unit in there that takes the air through with a UV cleaner, for example, and puts it back into the lift air as sterile air, then we could allow more people in there. But it's that kind of behavioural change which is we're beginning to look fairly seriously at. So people understand that with COVID around, they can't go back to their old ways. And the risks, of course, of coming back to a building without looking at it properly is that we're going to have sick building issues. You know, we're going to start the fans up and blow dust and dirt around. That's going to make people ill. A plant that we thought was perfectly good might fail suddenly and not work. The security issues, possibly fire safety, the fire dampers working all properly. We might be wasting energy, and we will if you go to full fresh air, of course, to dilute the COVID more. We will be using more energy and more carbon. And then what's the risk of someone coming in? Can we work out how best to deal with a possible COVID outbreak in an office or a restaurant or a bar or a gym for that matter? And how much is occupant productivity going to be affected by all of these extra changes that can take place? Water systems is a prime example of things to check. I'm not going to go into great detail here, but I've given you some good links. There's the HSE guidance on Legionella. CfD TM13 is an excellent document on how to design to minimize the risk of Legionella. ASHRAE Standard 180 is a risk-based assessment for Legionella in water systems. And then following that, ASHRAE brought out guideline 12/2020, which is managing the risk, which is more technical. So we would want our water systems, and I mention that because hot and cold water systems may have been sat dormant for best part of 12 months. We need to flush them, clean them, probably sterilize the system, fill them up again, and then have good quality water for people. So that's hot and cold water there. I scooted over that fairly quickly, but the same kind of thing for both hot and water systems, cold water. And then we think about cooling towers and evaporative condensers. They've been switched off for a year, and we've suddenly put those on again. We need to go through a whole process of cleaning them, making sure they're safe to use. BMS the same. If we shut down last year, did we take a record of all of the settings, the databases, schedules, set points? Are they stored on the cloud or somewhere? And then can we re-enter those? Do we need to change them? So there's a whole bit on building readiness guidance on the ASHRAE website there, which would be very helpful in making sure those things are implemented properly. So we may also want to change the way we've set the ventilation up so that we pre-purge the building before people arrive, and the advice is to start 2 hours early. So we're bringing outdoor air in, and we're flushing the building ready for people to arrive. And when people arrive, we go back to the occupancy routine. But then at the end of the day, we continue to purge for another 2 hours so that we flush the building of any COVID that happens to be left behind by anyone in the building. So these, again, are going to have implications in terms of energy usage, but they are necessary in order to keep the building ventilation clean. So there's more on air cleaning there, and looking at possible UVC. Obviously rushing a little bit today because I wanted to tell you about some of the other methods that we're looking at. We have to live with COVID. I think it's here for a long time. I said here it could be 2 years or more, but it could be forever, I suppose. It's certainly not going away, and as you can see from the numbers in the news and in the press, they are going up rather than down, and in some countries really reaching panic stages. I have my brother lives on the eastern side of Australia on the Byron Bay coast, and he and his friend decided to go fishing into the Pacific Ocean on a little boat, and the police stopped them. The police said, no, you can't do that. It's a lockdown. You have to stay at home. Well, I wouldn't have thought there's much chance of catching COVID in a small boat on the sea, but that just goes to show that society is reaching a kind of panic level here. And certainly in Sydney, in Australia, they did send the troops out into the streets to stop people leaving their homes. So we're certainly nowhere near normal yet. But we would like to get back there, and we need to do that with these engineering solutions that I'm talking about. So to make a safe environment, we look at contact transmission, which is on the left. So I won't dwell on that too much because it has been covered quite well by Public Health England and others in terms of mask wearing, cleaning hands, social distancing. But on the right, we in the UK have not done much of this, I'm afraid. America and other countries have. We need to look at ventilation really seriously. We need to sterilize the air using the UV, or we need to clean the air using filters. There's also a recommendation to control humidity better, which we just don't do in the UK. Very rare to get humidity control here, but if we can control it, it helps. And of course, mask wearing is the other thing that would help with airborne transmission. And just on UV for a sense, it does actually kill off the virus, and that was discovered way back in 1877 by Dowes and Blunt when they discovered that UV from sunshine was killing bacteria, and they got awards for that. But if you look at the picture there, what's happening is the UV light shines onto the DNA structure of the virus, and it breaks that DNA chain, so the virus essentially loses its code, forgets what it's meant to be, and it becomes deactivated and can't replicate and doesn't attack the human body. But you have got to apply the UV properly. Its optimum is 254 nanometers, as I've shown there on that graph. So if you use UV lights at a different frequency, it's hardly effective at all. So it has to be specifically at that, which, as it happens, can only be given by fluorescent lighting. So people offer you LED lamps, which produce UV, which they can, by the way. There are UV LED lamps. They operate around 220. They don't really kill any virus, so don't use them. And basically with UV, we draw air through a device with lamps in. The UV shines at the air, and anything in the air is hit by its rays and deactivated. It has to go at a reasonably slow speed. If it goes too fast, it doesn't work well, and it has to be relatively close, within 100 millimeters. We need to put filters in to keep the lamps clean, but we don't need a high quality filter. This shows how effective it can be. The top three samples are Petri dishes. These are dishes that are put out to catch particles in the air, and they're taken away to a lab so that the material can grow. And so they're all little growths going on, little colony forming units. And they were taken before the UV lamps were switched on in this particular room. Below it, 3 Petri dishes where the lamps were switched on. So the UV light was cleaning the air, and you'll see very, very few particles there. So much cleaner. This is a picture of a typical device made by a company called Midtherm, where they have the package in the center with the UV lights in there, and then they have a covering around it so that the lamps are hidden. And of course, we mustn't allow the lamps to be seen, because UV light is dangerous to people. You know, it would do the same to people as it does to these viruses. So we don't want it striking us. But they have a fan at one end which pulls the air in. It's got a filter module just to clean the air, the UV lamps themselves, and then the air is issued out the other end. And I just want to say there's 3 possibilities here. We could buy gadgets which do this, which I would call mobile. I've shown that on the left-hand side of this picture. So the mobile unit could come in a cardboard box. You take it out of the box and plug it in the wall, and it then takes the air through and cleans it. And that's actually quite a cheap, quick, easy way of doing things. Maybe £2,000 to do that with a good quality unit. I mean, there are cheaper units, but £2,000 would see you have a good unit, and you might need 2 of those for a classroom, for example. And you could do that, you know, in the morning just before people come in. The second solution might be the ceiling jet, which is over on the right there, where you put a unit in the ceiling, pulls the air up through itself, and then blows it back down into the room as sterile air. Now, if you try and do that, you've got to employ an electrician to come and wire it up, possibly a ceiling contractor to alter the ceiling to take the unit in, and then you've got to bolt it back to the structure above so that it doesn't fall down. So the costs go up. That's not going to take 5 minutes. That's maybe a half a day job. So you're going to lose the use of the room. So you're perhaps looking at £7,000 or £8,000 there for the same solution, the same deliverable, using that technique. And then the other technique would be to put it into ductwork for air being blown into rooms, which is shown there's a duct mounted unit. Again, a bit more work involved. You need a ductwork contractor to come and install it, electrician to wire it up, ceiling contractor to open up the ceiling to allow you to get in and do that. So possibly talking maybe £15,000 for the same kind of output there. So there are different levels of costs. It depends on the application, obviously, but the mobile plug-it-in one is a sort of quick, cheap, easy one to start with. Maybe that's the solution for people initially. But if you're doing a project where the system's getting built, as a refurbishment taking place, maybe the in-ceiling or the duct units are better in the longer run. Here's a mobile unit in position in a bed area in a hospital, in a ward. And you can see it's just putting clean air between those 2 beds to keep the air safe. This is one with my mother-in-law's care home. Actually, I got one put into that position in the corner there, you can see. So if you look on the left-hand side, the air is drawn in the bottom, up through the unit, across the lamps, and then blows out the top. So that keeps that room clean. So the care home she's in, which is close to where we live here, had 36 people, and of those 12 actually died of COVID, but she's okay. I'm not saying it was the unit that did that, but I think it would have helped quite a bit by at least keeping her air cleaner. And I was just reading in preparation for this meeting that the UK actually lost 42,000 people. 42,000 people in care homes died of COVID in the past year. So it's a big problem. But this kind of device will provide quite a good level of protection by cleaning the air in the room. What I would not recommend is mobile units that, UV units that shine the light out. So this is a Chinese device. It's in the corner there, and you can see the UV lamp, which is switched off, of course. It has an occupancy detector on, so if you come anywhere near it, it switches itself off, which means it's not working then, but it will switch on when you leave, of course. So it's really cleaning surfaces with no one in the room. But basically, there's a big risk there of UV affecting people, particularly a patient who happens to be lying in that bed. This is another application of it in a corridor, which we were looking at for the Nightingale ward areas, which, as you know, were not really used in any great quantity, but I advised against it because it's just too dangerous, I think, and wouldn't do the job properly anyway. And just finally on UV, I would say that ASHRAE has a lot of information on it. This is a whole chapter in the applications handbook on UV, amongst other things. So you will find a lot. So I'm going to move on fairly quickly. If you go into the website on COVID, there's a lot there on filtration and disinfection of air we're talking about. You'll find that information available to you with case studies, of course. And then finally, something I'm doing for dentistry at the moment in Birmingham, and this is with a medical group. We're looking at how we can improve the operation of dentists who at the moment are really hamstrung with long fallow periods between patients, because it is an application where they develop a lot of aerosols. It's what they call an AGP, an aerosol generating procedure, where the patient lies on the bed there, opens their mouth and breathes out a lot of aerosols. And there's a dentist and a dental nurse in the room as well. So what we wanted to look at was how we might control that. So I said, well, we should change the four-way mixing grill in the ceiling to a downward grill, which pushed the air down over the patient. And that's what I've got here. And that means that we can push the air downwards and avoid any of the aerosols coming up towards the dentist and the dental nurse. Once we've got it low level, we can pull it into an air cleaning device and we can deal with it. So just briefly, this is some research which hasn't been published yet, but will be fairly soon. And on the top left-hand corner, you're seeing a CFD model, which shows the air coming out of the grill and blowing around the room at 10 air changes an hour. The bottom left is showing the quality of the air, and it ranges on the blue to red scale from full fresh air, which is clean air, to stale air at the top. So you can see that this 10 air change rate is actually giving a very good dilution, and there's not much stale air in the room. And as you move to the right, in the bottom right-hand corner, it's showing you the droplets coming out of the face of the patient. So that chart is blue is very small to 20 is 20 microns. So the red and green and yellow are the bigger particles, and the blue particles are tiny, and the aerosols going around the room. So this just as a live illustration of this in place. So you can see this is a, whoops, that's a
Frank?
Yes, I'm back, but my slide stopped working. Look, I'm not sure I am for time actually, but I was just going to conclude that by showing how the airflow worked around that room, but my internet dropped out actually. So I'm back online. Hi everybody. And the dental work, which we're still working on, was looking, and this is really what I'm trying to say. As engineers, we go in and we can visualize the airflow we want. We wanted downward airflow to carry all the aerosols downward past the patient towards the floor, then take it into a UV air cleaning device and re-admit it back into the room as clean air. And that's working very successfully. But we did a lot of CFD modeling as shown there to demonstrate that that worked well. And that is what is going to be rolled out across the UK as a solution for dentists. So in the UK, we're at that stage now. The medical people in particular are very, very keen to work out solutions, and that's happening. I'm very sorry to say as an engineer that it's taken the UK, not just the UK government, I suppose, but the whole of all of us really to take so long to apply in engineering, but it is happening. And I'm sure many of you will be involved. I hope so, because we will need you and me and others to do this work in order to get back to normal. I think my time would be up, but can I ask if there's any questions? I've got the chat up. I can't see any questions in the chat. Does anyone want to ask a question before I finish?
Yes, this is Ijaz Shah from lush green city of Milton Keynes. You mentioned the 254 nanometer lamps of ultraviolet lamps.
That's right.
They will be only effective.
Yes.
So that's fine. We do have such lamps available, but when we talk about the refurbishing of the heat recovery ventilation systems, what is your suggestion? What would be the best approach to integrate these boxes of ultraviolet in the return, or should they be in the supply of the heat recovery ventilation system if we are thinking to refurbish them for reopening of the buildings?
Well, you could do either, but we are using these in some hospital wards now, and we'll put them in the return air because the COVID problem is in the room, you see. If somebody has COVID in the room.
Exactly, that's what I was thinking of.
Yes, but you could still put it in the supply because that air the return air will go to the supply to come back into the room. So if that's more convenient, you could do that. And we were even looking at putting it into branch ducts. So rather than have it on the main plant, you could maybe go down a building and have a UV air cleaner on every floor, if you had a branch onto every floor on the supply side. But the important thing is you clean that air before it comes back into the room. But it's often easier to put it in a return. At the moment, we are saying, no return, throw all the air away. But the cost, we will be seeing some very high energy costs, of course. And don't forget, the health service is aiming to become net zero fairly soon. They have a whole strategy document that they're going to publish in the next 2 months, ready for COP26, saying how the National Health Service will be net zero. So they're very, very keen on that. But I have to tell you, 50% of their carbon emissions are ventilation, heating and ventilation systems. So that's an enormous load.
Yeah,
and it's due to the fact that we are full fresh air. In the UK, we're full fresh air in hospitals. If we don't start recirculating, we will never get to net zero. So
right. Talking about the HEPA filters, would we, if we install in the fresh air intake, it would be too much expensive. So perhaps we can incorporate in return air as well, HEPA filters?
HEPA filters in return air.
No.
Well, you could do, because it will take out, if you're going to start recirculating, it will take out anything coming from the floor, such as COVID. However, anything coming from outside, because you've still got other pathogens outside the building coming in, they would mix with that clean air and go into the room. So in that case, you'd be better with them on the supply side. That would be the normal situation. And you don't put a HEPA on its own, of course. You have to have a pre-filter, a main filter, and then the HEPA is picking up the finest particles, the smallest ones. Quite expensive HEPAs, and of course it's a special installation that you have to do. You can't just stick them into the duct. They have to be properly bolted in so there's no air leakage.
A lot of modification required, yes.
Absolutely, yeah. And of course, they need to be installed by an approved person, because otherwise, if they leak, I mean, a small air leak around a HEPA filter drops its efficiency by 50%. You know, it just isn't worth having it in. So that's why you do that smoke test when you've had it fitted, just to make sure it's properly sealed up. I mean, the filter itself might be fine, but you have a small amount of air going around one of the edges or through one of the corners, and it's just ruins the whole effect. So HEPA is a good solution, but it needs to be applied properly. And you will have an ongoing maintenance cost of changing that. But yeah, these are the measured at our disposal, and as engineers, we can choose them. So thank you. Good question there. Thank you. Any further questions?
Yeah, Frank, I had a question. You mentioned early on about emerging technologies, and we've had a couple of presentations by ionization technology people. What's your view on the effectiveness, and is anybody doing any research to prove whether they actually work or not? Because again, it seemed like another magic bullet, or someone selling snake oil. So you know, we were skeptical because that was the sort of advice that was coming back from Cfd and ASHRAE. But do you have a professional opinion on where you think that technology fits?
Yeah, I mean, we on the ASHRAE group, we're calling them emerging technologies because we think they are a solution that could work, but we think we're not there yet. We would be worried about applying them widely in case there are other issues which we are not fully aware of. So, for example, ozone, for example, is highly toxic. Hydrogen peroxide, which we would spray in as a disinfectant, works well, but of course, if anybody breathes that in, they're as good as dead. Both those things have adverse effects on plastic surfaces. So if you're using them in rooms, you find the plastics deteriorate fairly quickly. Obviously, like putting something out in sunshine all the time, I guess. So there's lots of other impacts of these technologies which have to be researched. So that's our advice. There's a big bit of research taking place in Bradford at the moment where they've got 30 schools, and 10 schools they're putting UV air cleaners in every classroom in 10 schools. They're putting HEPA filters into 10 classrooms of other schools, and then finally they've got 10 classrooms where they're doing nothing, so they're placebos, and they're going to do this for a whole year and see how they get on. I said to him, it's a bit long to wait for an answer actually, but I can understand why they're doing that research, and dare I say, it's perhaps the difference between scientists and engineers. If you're doing science, you do have to take things carefully and study every aspect of it. As engineers, sometimes we've got somebody saying, we need an answer this week, please. We're going to occupy the building next Monday, and I want to know what to do today. So, you know, as engineers, we approach it with the best knowledge we have. We try to use certainty. We don't want to take too many risks. So what we know works, we apply. But coming back to UV, for example, there isn't any standard at the moment. So that light frequency is something I didn't really know too much about until I got involved. So I formed a committee which is going to work with the British Standards Institute to produce a standard for UV air cleaners. At the moment, there isn't one. You know, people will come to you with all sorts of devices, and you think, will this work? Does it do what it's supposed to on the tin? I don't know. And there's nothing you can compare it back against. So we're kind of developing a standard at the moment for the NHS, because they are beginning to use these devices. And then I said, well, it would be good to take this forward and do it as a British standard, so everybody's got the benefit of that. But that's where we are. That's what COVID has done to us. It's given us this big problem, and we have to develop these solutions as fast as we can. And because these things could roll out and you could literally be using thousands of these devices, we don't want to get it wrong. I would say be open-minded at all times. Anything could work, but you know, try one, then maybe try 10. But before you start trying thousands, you want to be sure that it's actually going to work today, tomorrow, and in 10 years' time, for that matter. So yeah, it's a big challenge for us as an industry, isn't it? Just dealing with COVID and making people COVID safe forever. And besides the technical stuff that we've talked about here, there's the cost, isn't there? You have to keep maintaining these things and replacing them and upgrading them. That's going to be an ongoing maintenance cost, which we have to deal with as well. But that's the era we're in, I'm afraid. So that's the challenge to us.
Thank you.
Okay, Frank.
Yeah.
Do you think the sick building syndrome will increase because they have not maintained the air conditioning system in offices? And when people go back, if it's not properly commissioned and maintained, that will create some dust and distribute and create some sort of health on the bad health on occupants. Is that true in your opinion?
Yes, most certainly. When you think about it, the only buildings that really shut for any length of time are schools. During the summer holiday, a school may shut for 5 or 6 weeks, but even then the janitor is going around checking things and running water. But we've just gone through a year where people have shut, more or less every building in the country, haven't they? These offices have been closed for 12 months. Now, maybe some of them have had a facilities team that have gone in and checked things, but many of them maybe just shut the door and went away. So when you go back and switch on, you are definitely going to be pumping a lot of dirt and dust around the building, and that is going to give rise to other respiratory diseases, maybe not COVID, but there's a lot of other airborne infections. In fact, the National Health Service is getting ready for a high amount of respiratory illnesses this winter from children through these very things. In addition to COVID, that is, they're saying respiratory illnesses are going to be much higher. But you're right, there's water as well. If you turn water on and you're the first one of you to go back into an office and you see that tap and you think, I want a glass of water. Are you gonna run it and you're gonna drink it, or are you gonna run it for an hour and drink it? Who knows? Should the system be sterilized? So if you go on the ASHRAE website, we've set out there all the procedures that people should go through so that they're building safe. It's a hell of a responsibility for a facilities team, really. All those people going back in to their buildings to use them and relying on the fact that everything works properly. And as you say, Maru, it probably doesn't. So you have to almost recommission it as if you just finished building it. And it's a brand new building. And for the first time, you want everything to work properly. So yes, good point. There's lots of risks around sick building, I think, in all of our systems. Buildings are complex. They've got a lot of complex systems in, and we need to check them out.
Thanks very much, Thank you. I think Darren will get the results in about 5 minutes. So
okay.
We got Frank. So if you got any questions, please ask Frank.
Just if you've got a couple of minutes, I would say that ASHRAE is hoping to have its Las Vegas meeting face-to-face. That's in January. All the committees coming together again. So that, at the moment, it looks like that's going to happen. The ASHRAE headquarters building has moved, as you know. It's now it's still in Atlanta, but it's on the edge. It's a new building, a refurbished new building, and that is due to open on the 1st of October to staff and others. They're coming back to work after COVID. The COVID numbers in the Atlanta area and Georgia are quite high, actually. They have similar problems to ourselves, I'm afraid. But they have put a lot more engineering effort in, and we're behind on that in the UK. The other thing is that ASHRAE has formed a decarbonisation committee. It's a decarbonation of buildings, and that's I'm on that committee, and it's working really hard. I'm really impressed by the different subgroups and how they're tackling building systems, grid interactions, thermal storage, all these different solutions that might help us get carbon down as a drive towards zero carbon. Nothing's published yet, but if you go onto the ASHRAE website and put that in, you'll see it on the front page, and it tells you what's happening there. And then the subcommittees are meeting if anyone wants to tap in and join them to see what they're discussing. But that's a recent initiative by ASHRAE, and I think it's going very well. There's certainly some very clever people on it, and I'm impressed by what they're achieving so far. The COVID crisis did impact upon ASHRAE's publications, unfortunately. So the publication I worked on net zero hospitals with ASHRAE, that's still not been published because everything got stuck in a line. The emphasis we put on the COVID information, which I've been talking to you about, which has been brilliant. Of course, there's a lot of good stuff there. But some of the other stuff in the pipeline has been delayed, which is unfortunate. But you should start to see those publications rolling through fairly soon. So it's been a difficult year for us all. I think ASHRAE has risen to the challenge quite well, put out a lot of good data. For me in particular, it's been quite an interesting experience. I'm on the ASHRAE schools group, for example, for COVID. And about 6 months ago, it was announced that the American government were going to spend $110 billion, that's 110 billion, putting air cleaning devices into every classroom across America. That's UV air cleaners and filters. And to make sure the ventilation was right and clean. I discussed that with the Department for Education in the UK, and they said they were not going to do that. They didn't want to do anything. So we still aren't doing much in schools in the UK, although there is this research work being done in Bradford at the moment. That's been led by Leeds University. But the problem is we've got schools starting back next week, some schools this week. So have those children got to endure another winter of open windows, with their Eskimo jackets on? I don't know. It seems that we need to try and get back to some kind of normality so people can get on with their life and not have these issues, not try and study at home. They need to be face to face. So for me, I've kind of lived on two planets. There's planet UK, where we struggle to really get started, and there's planet ASHRAE, where there's loads of solutions being applied, and people have got back to normal a lot quicker. So I do think it's in our hands as engineers to make sure the ventilation is better, is cleaner, and people can meet and work together. And if someone with COVID enters the room, the viral load is reduced and maybe removed altogether by the equipment, and the chances of it spreading are much lower, and particularly with a vaccine, because with a vaccine, I believe the viral load you can take is a sort of reasonable one. So if we can reduce that viral load, then people are safer and it won't spread as much. So the experience has been interesting, but also upsetting, really. I would have liked to have seen the UK do a lot more, but I think it's beginning to come through. And I think in all your work out there, in the businesses you work with and the opportunities you have, you will probably see that people want you to come up with ventilation solutions. There's one final point, Maru, is we do have a problem in the UK with competencies. As the Hackett inquiry said about the Grenfell Tower, it's difficult to know who's competent to do work and who isn't. And again, I see a big difference there with ASHRAE, where engineers are licensed and are competent to do what they do. And also with these courses, such as the ones I'm running here, where people can do the course and demonstrate competency. In the UK, we don't have any of that, so it's difficult to know whether someone talking to you about this is actually competent or they're just trying to sell you something. And we're talking to the UK government about that now. Can we run short courses which would basically accredit people as infection control engineers? We haven't got it yet. Cfd doesn't do it. ASHRAE does do it in the States, of course, but would that be accepted here? But I think as a country, we need to understand how we can identify competencies and make sure people are employed who know what they're doing and get the right result. So
I totally agree with you, Frank. As Gary put it in his presentation, we got the shortage of skills. If you have skilled people, you can rely on their skills. Sometimes you are not sure if they are salespeople or actually they have got a good knowledge. Frank, do you think that these UV and all the devices, they clean the air? So after COVID is finished, hopefully, could they provide a better air quality inside and outside the building as well? Because I've seen in London, they have put some devices that cleans the outside air, the pollution from the cars and everything.
yes, most certainly. This, UV, for example, will kill 99.9% of all viruses and bacteria. So it makes the air much, much cleaner. And it would, for example, reduce illnesses. So productivity goes up. Productivity goes up about 10%, actually, because the number of people off sick reduces, and people also feel better, so they can get on with their job, get on with their lives. So yeah, we are entering an era where air quality is going to be taken much more seriously, and I think you'll see that now that we will have to make sure that people, that we engineers are able to deliver the air quality that people want using these devices. So yes, good point, Maru. Good.
Okay, thanks very much. Any other questions? We got another 2 minutes. Yeah, Frank, how do you see the decarbonization and better air quality? How could we balance it, especially as you mentioned in hospitals, because they use lots of energy? How could we achieve zero energy?
Well, strangely enough, these air cleaning devices are the answer, because if we can, the UK is still on full fresh air in hospitals, and the air change rate is 10 air changes an hour. So every 6 minutes we change all the air in a treatment room. Wards, it's 6 air changes an hour, so that's every 10 minutes. But and that's all based on dilution, you see. Now, if we were able to recirculate the air by cleaning it with UV air cleaners, because we don't need 10 air changes for breathing, we only need 1. Then that would reduce the carbon waste dramatically. And I think that's what we're going to have to do. So it's a rather strange thing, because in America and other countries, they do recirculate air, but the UK doesn't. It's a historic thing. But this COVID pandemic is forcing them to look at that more seriously in order to clean the air for the reasons you've stated. But at the same time, it will help us reduce our carbon emissions as well. And we can apply that to other buildings too. So yes, they're connected in a way. I think the other thing that's coming out of the decarbonisation is renewable energy is all well and good, of course, but it isn't always generated when we want it. Wind power and solar power and those things. So we're going to see a lot more thermal storage coming in, cold water storage or phase change material for cooling, and then on the hot side, hot water storage so that we can keep the heat or the cooling for when we want it through pipe systems. So engineers will be able to look at networks of heating and cooling and tapping into those as and when they want them, and then using heat pumps to boost the heating temperature level. So you could have a 20 degrees centigrade water main around a site, and then you could put a heat pump on it to push that up to say 40 or 50, and then further along maybe other heat pumps which will push that up to 70 or 80 degrees C for hot water usage and the like. So we're going to see that kind of layering of energy distribution systems, and engineers being able to operate those in a smart way. So some of those presentations were excellent because they were really talking about how we can monitor energy usage and loads and tap into these smart systems so that we are able to use the energy instead of wasting it. What we do at the moment, if we don't want it, we kind of throw it away, which is crazy because tomorrow we might want it. So I think thermal storage and engineering are going to become a very important aspect of decarbonisation.
Okay, thanks very much. Any other questions?
Right, I had one last question on when you've looked at the air cleaning with UV and filters and stuff. Do you have any idea on what the energy penalty roughly is? So in terms of, you know, if you have to put UV lights on all your main air handlers and branches, how much does that add in terms of watts a square meter? How much energy do they use? And obviously the additional pressure loss from those devices on your air distribution systems. You know, going back to the, you know, reducing our energy, but if we're adding extra pressure drops to our systems, we've got to drive the fans harder, etc. So.
Yeah, sure. Yeah, I think with the UV, there's obviously no pressure resistance there because you've got space around the lamps for the airflow. But UV lamps are typically 60 watts. So over a day, they might be costing 5 or 10 pence a day in terms of energy cost. And 60 watts is, you know, so many kilowatt hours a week. It's not a high load. But the problem is we're going to have to use a lot of those in. If you take a school, for example, with 20 classrooms and you've got 2 per classroom, then you're up to 60 units. So it does tot up then over a year. So it will have an impact in terms of energy and carbon emissions. The benefit might be that. Sorry.
I was just thinking. You said in terms of, you said the airflow had to get within like 100 mil of the lamp. So
yes, yeah.
You know, on a big ductwork, you're going to need a lot of lamps in there. So it might.
Oh, yeah. Yes, yeah. On the ducted applications, that's different. You're still flowing along the length of the lamp, but so they're going in the direction of flow, and they may be 6 feet long, and you've got a whole bank of them, so you've got a lot in there. So you're using a lot more than 60 watts, but then that system might do a whole building on its own. The pressure drops on HEPA is quite interesting because a HEPA filter typically has a pressure drop of maybe 250 pascals, which for many systems is the equivalent of the pressure drop of the whole system without the filter in it. So you're kind of doubling the pressure drop. You can't just put them into a normal system that you didn't have one, because a fan wouldn't be able to take it. You'd have to put a booster fan on of some kind. So yeah, that introduces bigger air distribution loads, and again, that's more kilowatt hours and more carbon emissions. So these things are coming at a time when we want to reduce carbon, and we're finding there's a penalty. But at the same time, we perhaps want to be smarter with the air quality side of things. We don't need to use so much fresh air as we do, certainly not in healthcare, and maybe not in other buildings, because we've actually cleaning the air within the building. We still need fresh air, don't get me wrong. At the moment, in the absence of those devices, though, the advice is to go full fresh air for any building, like an office or anything, so that you're purging the building all the time of any COVID aerosols that happen to be generated. So that's a massive penalty, which has been imposed since COVID came. So these devices will help us reduce those. But the big message is we have a challenge as an engineer. We have things we have to do to make people healthy and safe, and we also have to try and do that without hitting that carbon target. We've got to keep it down.
Okay, Darren.
Hello, everybody. Thank you for your patience, and thank you very much, Frank and Maru, for keeping things going. Thank you ever so much. We haven't lost Frank, have we?
No, sorry, I switched my camera off. I can put it back on if you like. Just keep my transmission.
Thank you for keeping things going. Okay. I realise we overran there, but I really appreciate it.
That's all right. No problem. No problem. We had a good discussion.
Oh, great stuff. Okay, so I've been summing up the scores, and the results are in, I think, as they say on the telly. So, I mean, first of all, I think, once again, just a big round of applause to all of the students for their effort. Their presentations, absolutely. So from the results, we have So we take a look at the undergraduate and master's presentations. And in terms of positioning, we have in first place, it comes with a certificate and £250 prize. We have Gary, I've lost your surname, Gary, apologies. Gary Parker. So well done, Gary. And in second place, we have Catherine Young, second place, which is a prize of £100.
Thank you.
And in third place, we have Zain Abidi, third place. So well done, Zain. That comes with a certificate and a one-year ASHRAE student membership with 1 year Smart Start program for you. So congratulations. And on to the PhD. In first place goes to Ahmed Al-Adawi. Congratulations. And once again, that's a £250 cash prize and a certificate. In second position, in second place came Joshua Vasudevan. So congratulations, Joshua. And again, it's a £100 cash prize and a certificate for you. And in third place, Amir. Congratulations, Amir Silvan. So some fantastic presentations delivered by everybody. And once again, thank you all. Really like to thank, obviously, everybody for attending and for our judges and for our life members of ASHRAE. It's been a good event, and as I say, some great presentations by everybody. So thank you ever so much. Maru, is there anything you'd like to say?
No, I would like to thank all the students for participating. Well done, Gary, and all the other students. That you all did very well. I would like to thank our judges. Thank you very much, all of you. John Brittle and Ben are here, and also our life members. Thank you very much, James. You are still in the classroom. We can see you. Thank you. Yeah, well done, Ahmed. And thanks, Joshua, for organizing and helping out. And thank you, Darren, for chairing and doing everything. Thank you all.
Thank you.
Very good. Very good. Thanks very much for everything. No problem. Appreciate it. No problem.
No problem. Thanks very much. Thank you.
Thank you all.
Thank you all. Thank you. See you soon. Take care.
Thanks, Maru. Thanks, everyone.
Bye. Bye.
Good luck. All the best. What's that?